Oops. Mic check one more time. Boop 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 boop.
It's working.
Yeah, mic is good on my side.
Yeah. Okay, mine too. Trying to make sure the balances are sounding good. And alerts aren't too loud. Someone throw something at me.
All right. See you on stream.
Yep. See ya. Thank you.
Okay, now I have to go onto your stream and throw something at you. Someone already did. Okay, someone did already. We're good.
Yeah, no, we're good. We're good. Oh boy, we got a lot of people. Let's see. Let me make my hellos. Hello, Calcium. Hi, Komi. Hi, Tyler. Hi, Calcium. Hi, Tyler. Hi, Calcium. Hi, Tyler. And then, yeah. What's your usual? Wait, is this considered collab? Right? Let me set up collab.
Oh, yeah, we can do a shared chat if you really wanted to.
Absolutely. That's the whole point of a thing like this.
Yeah.
Heck yeah. Let's see. And then we'll actually do like another kind of like collab like this in the future. Like just we'll play something. I really want to play something. Pen might be a little quiet. Well, now he is. Let me click you up. Well. Look at who else is here.
Hello.
Oh my goodness. Hello, Possum. Welcome in. Thank you for the raid. Welcome in, Raiders.
I sent you a collab invite.
Okay.
And you guys cannot see, but 𝖘𝖈𝖎𝖕𝖕 is also here.
I'm here.
Do you have a Fugi by chance? Do you know how to set that up?
Yes, I do. I have like a bad one. Hold on.
That's fine.
Hold
Just get something up.
Okay.
Just get something up, because I think it'd be cool. In fact, let me.
Wait, where did you send the what?
Nothing. 𝖘𝖈𝖕 should be able to. 𝖘𝖈𝖕 should be able to do something like that.
Oh yeah. Where's 𝖘𝖈𝖕? Okay, there you are. Anyway, while we're getting set up,
Yeah. You're what? Oh, he deafened. Okay. Well, I guess for the few people that are here with me that don't know what's going on, I guess I'll do my intro. Is that all good?
Are you asking me?
I don't know. You're here.
Oh my god, yes. Do whatever you need to do. I'm not even live.
Okay. All right. Well, I guess I don't need to mute for that. But hello everyone. My name is alephmuvt. I am with currently Penn Center and 𝖘𝖈𝖕𝖕𝖕, two other fantastic math streamers that we are all going through and chipping at the current videos submissions for the SoME Summer of Math Exposition. It is gonna be pretty chill. We went through a lot so far already, right? So I'm planning on doing. I have 3 collabs in this regard with Penn Center. Then later on, I have one with Gaussian Surface, and then another one with Poisson. So let's look forward to that. Poisson.
Which channel should I direct my chatters to?
oh my gosh, 𝖘𝖈𝖕, you are huge.
Oh, sorry.
No, that's okay.
Oh, you
That's
meant
just
like my image.
Oh my gosh.
That's true.
Volume.
Yeah, you're good. You're good, bro. You're good.
Just the loudest man ever.
It's like no, you're fine.
Wait, where are you at? Shoot.
Oh, do you need my thingy?
I think so.
Here.
It should all like line up though, right? Oh no, absolutely not. Yeah, I need another one.
Here. Hopefully that works.
Yeah, I know. Polynomial wishing effect on Alephs is so cute.
Ah, thanks. It's really good.
Who did someone draw that for you? Like, it's such a cute little drawing.
Yeah, 𝖘𝖈𝖕𝖕𝖕, one of my friends, made me that. It's really cute.
Wait. Do they have pen in their name?
Pen? 𝖘𝖈𝖕𝖕𝖕.
Okay, they're like 10 out of 10 in my books, automatically.
Yeah, she does a lot of like pencil drawing, so she made that for me. Uh, there you go, Damie. I got you now. All right,
Yay.
I'm all set with you guys. Okay. I have the video prepped, also on YouTube, so we can go ahead and get started with this one then.
A trusty pencil, which is weird to say because I am pen center, but that's okay.
All right. Ready to go?
Ready when you are.
All right. So this one is called the endogenous design mismatch. This video explains why digital platforms are technologies and often designed around specific average user, even though people differ substantially in their skills, resources, constraints, and ability to adapt. That's a synopsis. We can go straight into it then.
I'm gonna have a million thoughts on this.
I also don't know what that word means.
So weird. I haven't heard it before for this type of thing.
Endogenous. Yeah, I wonder what.
I might have to go look it up while you
Digital
guys are starting to
platforms
play.
are often designed as if every user were the same. But
Can we get captions?
people differ in their skills, constraints, and the cost of adapting to new technology. When one design is imposed on everyone, what works well for some can quietly exclude others.
I'm gonna make it a little faster too.
This video explains
Yeah, you can
how
bump that
that
up.
design mismatch emerges, why market may not correct it, and what policy can do about it.
Imagine two people trying to use the same digital platform. For one of them, more sophistication is valuable. Advanced features, customization, and greater flexibility make the product better. For the other, however, exactly the same sophistication can become an obstacle. More menus, more settings, and a more demanding interface can make the product harder to understand and operate. Now, suppose the company knows this. It could design a simpler product for most users to use. Or it can deliberately build a more sophisticated product that is especially valuable to advanced users, even if everyone else stops buying it and using it. And then that gives us the central question of the paper. Can profit-maximizing product design itself generate exclusion, even when society would prefer a more inclusive product? To answer this, I built the simplest model that contains this trade-off. Normalize the total mass of users to 1. A fraction mu belongs to 0 and 1 range are high-capacity users, type H. The remaining fraction 1 minus mu are low-competitive users, let's call it type L.
Mu.
Then the company chooses one product with sophistication level X,
I already
where
have so
a
many
larger X means
thoughts
a more
on
sophisticated
this.
product. It also chooses a uniform price P, which
Do you want
is
me
zero
to hit
positive
pause real
price.
quick?
Let V_H_𝖈𝖗𝖊𝖎𝖃 to pay off a high competitive
Yeah, sure.
Yeah.
Wait, are we doing like the supply demand curve here? Is this what's happening?
I think this is like an extreme oversimplification of the question that they were trying to answer.
Yeah, it looks like
Wait,
it's.
what are they trying to answer first and foremost? So
they're-
that we're on the same page
like-
here.
Trying to hit a sweet spot between the viability of users and like the competency of the user. I'm not sure. Like, who are they designing it for?
I was gonna say it kind of sounds like they are trying to like address the problem of, you know, different people have different needs when using software, and those needs are like clashing. But maybe Aleph's is closer because like low key they're only talking about like one factor, which seems to be like on a scale. So definitely not at all addressing the, you know, large question that I thought they were going to.
Yeah, I think it's a little more
it'd be
simple.
like a really complex. It'd be a complex system, right? But I think they've tried to simplify it into like a linear kind of problem, where like the sliding scale, like based on that little graph they had, right? The sliding scale of like some users are going to be like, no thanks, and like that's the one that's kind of down and to the right, and then some users are like,
Yeah.
heck yeah, and that's the one that's up and to the right. Is that what I'm like getting from this?
Yeah.
Yeah, I think that is.
It's a thing you can do. It's a picture you can draw. Is it useful to software development? I'm not sure about that.
Yeah.
Well, I guess like it's a maximization problem, I suppose, but can it be the simplified?
Yeah, I think that's the real question. It's also like, you know, can you just say, this is how simple my software is? Like, I don't know if that's plausible to do.
Right.
Uniform price P, which is greater than 0, positive price. Let V_H_𝖈𝖗𝖊𝖎𝖃 to pay off a high competitive user, and V_L indicates the willingness to pay off a low competitive user. The central consumption is simple. Sophistication helps one group and hurts the other. So therefore, we do have this v prime of h greater than 0 and v prime of l smaller than 0. So a more sophisticated product creates more value for h users but less value for l users. Okay, then question, who buys? A user buys whenever the product is worth at least as much as the price. So type I buys when v underscore I greater or equal than p. Suppose sophistication x cost forms C, with C increasing and being convex. Profit is therefore price times the mass of buyers minus design cost. Here goes our formula. At first, this looks like a two-dimensional problem. Choose both x and p. However, there is a much cleaner way to solve it. Let's suppose there are three possible markets. There are only three economically distinct possibilities. The firm can sell only to low competitive users, only to high competitive users, or to both groups. Then, why serving everyone is different? If both groups buy, the uniform price must be acceptable.
Misleading.
Okay, so that was a bunch of jargon right there, and I will admit, and some of you guys might don't know this, I'm not the best at stats. So any sort of like normalization or statistical analysis, like this bit, kind of flew over some of my head. So what happened?
Which is very economics.
Yeah, it's a lot more economics than it is statistics, I think.
Okay. I just want to look back at the equation because that was a bunch of stuff that got thrown in. So now we're creating a model, and now we're trying to optimize for what now?
Like the willingness to buy, I think. So, you know, there's a sweet spot of, okay, well, we want the people
and price
who they have like inverse relationships or whatever. I don't think it's that. I wish they put a graph in there about it, at least if they're going to put an equation. Maybe they do later.
I was like, I'll probably slow it down just a little bit, like 1.25.
Yeah, they were talking very slowly earlier. It's so fun.
Yeah, let's.
I also sent you a shared chat invite.
Sent me the shared chat invite?
I think so.
Who's really in charge?
I don't know.
Yeah, let me find it then.
Choose both x and p. However, there is a much cleaner way to solve it. Let's suppose there are three possible markets. There are only three economically distinct possibilities. The firm can sell only to low competitive users, only to high competitive users, or to both groups. Then, why serving everyone is different? If both groups buy, the uniform price must be acceptable to both. The highest common price is therefore determined by whichever group has a lower readiness to buy. So profit from serving both groups is, the formula goes this pi underscore b, both stands for both, equal to the minimum of v underscore l or v underscore h minus the design cost c. This minimum is the core of the model. If one group values the product at $100 and the other at 60, the firm cannot collect 100 from one and 60 from the other. With one common price, it can collect at most 60 from everyone. Now, compare this with social welfare. Price is only a transfer between users and the firm, so it disappears from the total value. If both groups are served, welfare is w underscore both stands for b equal to mu v underscore h plus 1 mu times v underscore l and minus c.
What is our target audience here? Is this like undergraduate, graduate level math?
I was gonna say this would make a really nice presentation if you're working for a firm.
This would be like, okay, so you actually don't care about design at all, and like you just want to create economic value out of people like arbitrarily, because it's like it's not really a great economic argument because it's so simple, and it's also just not a design argument at all because it's not design.
Kip asks, is this real math?
Yeah.
I don't
know, man.
Seems a little arbitrary. Yeah, I'm like, I'm picking up I understand the first bit here. You know, there's only so much value you can get out of this, but like the other end is like, what? What kind of model is this?
If we were really going to talk about like, there are so many complex creations of value from like their quote unquote society value that like you could potentially mathematically model, but like it's definitely not just that.
And they've picked a particular, they've picked like a convex model here too, because I see like the mu and the 1 minus mu with the VH and VL.
Yeah, it's been normalized, right?
Oh, okay, that's why, okay.
I'm still confused what the goal is here. You're right.
Here, A greater than 0 measures how strongly high competitive users value sophistication, and C greater than 0 determines how costly sophistication is to produce. the two valuation curves cross each other when 1 minus x equal a times x. So there we have x lowercase b equal to
Like how we have
1
no
over 1
units
plus
in
1,
this video
a, 1
at
plus
all.
Yeah, I don't know what these
Now, let's
axes
look
are
at
saying
a
anymore.
numerical example of inefficient exclusion.
How
Take
costly
a
really
equal
hoping she would
2.5,
talk
b
about
equal to
concrete.
2.1, and mu equal to
Mhm.
2.43.
Yeah.
If the firm targets low
Well, that
competitive
would be
users, it chooses x equals 0 and earns pi star underscore l equal 1 minus mu equal 0.57. If it serves
did
both
pi
groups,
L
the
come
valuation
from?
curves cross at x equal 0.4.
Mu.
Both groups then value the product at 0.6, so the firm charges price p at 0.6 and earn a profit of 0.1592. If it serves only high competitive users, it chooses a maximally sophisticated product, which leads us to x equal to 1. High competitive users value it at 1.5, so the profit is actually 0.595. It's larger than the previous one, and strictly larger than the previous 0.592.
But how many H users do we have?
Okay, so exclusion is not
Yeah, also this is
automatically
just,
inefficient.
if it's about
Right?
software, there's
The
so many
model
other
does not say that
metrics that you would
exclusion
be
is always
talking about, like
sufficiently
conversion
harmful.
rates
Suppose
of
adoption
users
type
and like
I also
people.
creates an
It's just like
external
so
effect, which we denote as
business.
E underscore I. Then welfare under broad adoption becomes this formula as you're seeing right now on the screen. If E underscore L is positive, inclusion becomes more socially valuable. If E underscore L is sufficiently negative, exclusion can itself maximize welfare. So the theory is not inclusion is always better. It actually tells us exactly which private and social objects must be compared. Okay, now moving on to the next topic, we discuss whether training can change who is excluded. So the next extension we're talking right now introduces capacity investment. Let tau greater or equal than 0 represent training, onboarding, education, or interface assistance. Effective evaluation becomes this formula you're seeing right now. Training shifts users' ability
How are
to
you
work with one
abstracting
product.
this stuff?
A sophisticated product that would otherwise exclude some users
Yeah, I feel
may
like this
become
is like a
accessible to them.
presentation I would
Because
have
both
seen
groups
at like
are safe,
graduate
and low
level,
competitive
and like
users
when you're
determine
doing your
the
like
common price. Then
presentations to
the
other
firm
people.
values a marginal increase in training through B prime underscore L, because that is what relaxes the binding price constraint. The planner values the gains received by both groups, and here's the calculation formula for that. Therefore, the social planner's marginal benefit exceeds the firm's exactly when B prime underscore H exceeding B prime underscore L. Under the regularity conditions in a paper, that implies more training under the welfare benchmark than
It's
under
almost
private
like
choice.
if you took like
Again, underinvestment is not
a document
automatic.
and then just
The
read the
model
whole
gives a
document
precise
out. Like
condition under
I
the given
cannot tell
curves.
what's going on at this point.
Okay, now let's talk about innovation over time. The same mechanism also has a dynamic interpretation. Let's say x underscore t be sophistication at time t, and
I
I
feel like
underscore
she
t
knows what she's
representing
talking
the
about
innovation
reasonably
investment.
well.
And let's
But I
have
don't
this
think she's
formula x
conveying
underscore t
that
plus 1
knowledge
equal to
really
x
well to
underscore
the
t
audience.
plus g of I underscore t,
That's
where g
that's
is a
true.
function that is increasing and concave.
I feel
Innovation
like it's also
pushes
just
the
like
technological
the
frontier
premise
forward
has not
and
been
towards greater
answered.
sophistication. And training actually moves users' effective competitively upward, so they both operate on different sides of the same mismatch. Okay, then next question we would naturally ask, can policy remove the mismatch?
Stop.
So we ask in this paper
What's
whether
that? So, okay, where are we at now? Because I think what it's trying to answer is that there's a bunch of different things, and I'm not like again. I don't even understand how they're like abstracting the idea of like a quality product in all of this. This looks like the context is way above what we should know.
I think it reminds me of like in engineering, this is like a much simpler thing, but like sometimes what people will do is they'll make like a decision matrix where they'll take something like weight and then like of an object you're designing, and then they'll turn it like on a scale from like 0 to 1 like as a parameter, and then like mark it against other parameters like very arbitrarily to create some kind of like this is what we should prioritize and stuff. So I feel like this is kind of doing that with like, but with innovation and with like really complicated things, which I don't really know how you would do that. Like, what do you mean rate to produce innovation? Like, how do you measure that?
Yeah, and yeah, we're getting
We might be getting snake oiled. We might be. This could be true.
We're getting hustled. We should expect that this is like a great thing, a great product. We should buy.
It's low-key giving AI like.
Yeah, I guess I just can't say anything about the math of it, because what are we talking about?
Yeah, either I'm missing something, or this is like just way past what I'm able to actually comment on.
Yeah, having nothing to say is worse than like having bad things to say.
Bad things to say, I agree.
Through transfers, that R belongs to either low or high or both types, denote the three possible market regimes. regimes. If pi underscore r of x is firm profit and w underscore r is welfare, let's define the regime-dependent transfer as t equal to w minus pi. The firm's modified payoff then becomes the formula you're seeing right now. So, in principle, an appropriately designed transfer schedule can remove both the targeting distortion and the sophistication distortion. This is an existence result, not a claim that such a policy is always
Do
easy
you
to
think so,
implement.
Possum? She's going to sell us something
So
at
let's
the
just
end.
be clear on that.
I'm really
Let's
hoping
recap
there's like a
the
sponsor.
synergy of
waiting
this
for it.
research project.
It's
Can be
gonna be
summarized by this
sold.
comparison. When a monopolist serves both groups at one uniform price, the private value of broad participation is governed by the lower willingness to pay, but the social value of broad participation
But like we're
depends
talking about
on the value
design.
created
You
for
don't even need to pay
everyone,
for certain
not
software.
the someone who uses the product. Because those are different objects, the privately optimal product need not be the socially optimal one. And because sophistication changes the two groups' valuation in opposite directions, the disagreement can determine not only how sophisticated the product becomes, but also who remains in the market. More broadly, digital technologies can expand the set of opportunities available in principle, while product design, competitive, and complementary support can determine who actually get to use those opportunities. To summarize, essentially we are talking about an endogenous design mismatch.
Good design
That's
does
it.
not ask everyone to adapt in the same way. It
Yeah.
actually recognizes that people have similar skills,
Yeah.
face different constraints,
Good design is
and
good
also bear
design.
different
Okay.
fruits when a technology changes.
This didn't talk at all
And
about
markets
how to do
alone
design.
does not always
What is this
deliver
B-roll
inclusive
as well?
design. But you know what? Better incentives,
Why did it get so much
standards,
slower?
and
Like the
public
voice acting.
policy can help. Closing that design gap is ultimately a choice about whose needs count and who gets to participate.
So that said nothing to me.
This gave us a whole lot of like jargon without actually explaining why we need to understand it.
I would say this video scores negative for me.
I
Because I thought we were going to talk about like racial justice and design and the other things that people talk about when they talk about good design these days, but this was let's do economics on it. Which was
I think the attempt was there, though. Like, I think, to me, I feel like it just flew over my head, right? Like I think she was trying to discuss that, but didn't quite get it across to the audience what she was trying to say.
Yeah, I think it does to me become dangerous when people present these kind of topics as mathematical, because I did a presentation on this, but like we tend to view mathematics as like this neutral thing, right? So if we can abstract, design, justice, and all these other difficult topics into this neutral mathematics, then we automatically get all our problems solved. But like in reality, we're making all the decisions about like what it means to be sophisticated or who gets access to the software or whatever. So like trying to pose that as like the solution for design is like worse than doing nothing, in my opinion.
I just couldn't get it. I
mean, that's also true. I don't think the video was very understandable.
I feel bad because I'm gonna be writing this review, but like, shoot, that's not how I didn't understand what our purpose was. I didn't understand why we needed to abstract it this way. What research or what sources are we like using to like prove that this math would work out? I would just have to take it at face value. More importantly, like I have no credible insight as to like why this would work.
Does she cite any papers in her like little blurb?
Let's check the description. No description added. Okay. No.
Well,
I can't say anything good about this. I just learned nothing, or if anything, I'm just more confused.
Yep.
It's like, and in terms of just like as a video, like this is something that I've watched, and now I feel like I wasted time. And we're grading it on like how well some of these videos make the impressions, right? Do we learn something? Like par would be like a 3 or something, right? Or no, like right down the middle.
Yeah, about the same as what 5-ish.
Yeah, 1.5.
So like I definitely lean on the other side of 5. I think that I would say that I think the story, like she kind of has the story, I think, but I don't think that the mathematics that was delivered was accessible to the audience, or was like, and because it wasn't accessible, it just didn't really help prove kind of what I think she was trying to do.
Yeah, I feel
If that
like
makes
to me,
yeah.
like you would either, if I was trying to recommend like somebody to like learn about this, I would either say like go read like an economics book that's like written on it, or like go read like design sources. Like I feel like this video doesn't really have like a useful perspective, I guess, like on it that's like unique, you know?
Yeah. I forgot the grading scale on these. Who's done some of these so far?
Oh, I just vibed.
He just vibe codes his feedback.
Yeah, I would say like I was somewhat interested.
Like, I mean, you said you felt like your time was wasted, so I think that's a pretty good indicator of what the rating should be. Like, I mean, it's, you know.
Right. I just
See,
remembered
I
the
know
guidelines.
Suki put this somewhere here. Oh, here. So guidelines are motivation, clarity, novelty, and memorability.
Ah, okay. Where is that at?
It's under the, I think, homework at the top of the homework channel in the
Ah,
Discord
excellent.
server.
Okay, yeah. Now I can grade this. Yeah,
Yeah.
motivation. I would say.
Oh, Suki says if you press help, you can see the official guidelines too.
Oh wow.
Where's the help button? Oh, there it is.
Oh. Duh. The only thing that was interesting was the motivation to me. I will be honest. The clarity was not there. Novelty. I mean, I don't know why we were studying the economics of it, or what makes me interested in it. And then memorability. Like I actually understood less. And that's just me being a little critical, I suppose.
I think it's a fair criticism. I think the question that the creator's asking is actually really interesting. I just don't think that what was brought to the table to support that hook was helpful to any of us that were watching it, right?
Yeah. And this doesn't even like give us perspective on like the actual technologies we're talking about. Like what kind of product are we talking about? Are we talking about like just the tech sphere? Are we talking about like software development? Are we talking about like app development? Are we talking about the technology itself? Are we talking about like smartphones or blenders or something like that? I don't know.
Yeah, exactly. I think like I think you've summed it up by saying a concrete example of a technology would have been really nice to have right at the start.
I thought they said software, right? But I mean, it's pretty general.
It said firms. But the way they're phrasing it was like who's buying a product. But I'm thinking
But firm is just like the company that's doing the thing, right? Like firm doesn't really mean much.
I think they were. I think they had talked about the complexity of the software. I unless I was like just inceptioning that into my brain, which I could have been.
Yeah.
Well, I'm sure software is a piece of that too, right? Like it's one example. Yeah. But there's other design things, right? Like, oh, how are they going to design this walkway or something, right? Like, I'm sure.
Yeah. I think it does make maybe a different case if they're targeting software, just because of the current landscape of things. Like, I could see this argument being more interesting to someone interested in software rather than like, I mean, I can speak at least from an engineer's perspective. Like, this isn't really how we would talk about this stuff, like, to an engineer. So in terms of target audience, like, it might connect better with the target audience.
How do you spell layman? Oh, thank you for following Polynomial Possum. Given the average person, or just the average video. Some examples.
Yeah, Possum makes a good point. Like, at least they're in the right target audience, I think, which is undergrad and grad, and it's not like middle high school or anything like that. So
yeah, I suppose
for sure.
Yeah, this is a very economical discussion, but
I think it's a little crazy for undergrad too. But I mean, maybe if you were in like economics, it would not be that bad. I'm just not that dude.
Yeah, like this is probably like macroeconomics level, right? Like this is
Yeah.
probably like a middle macro is where I would probably place this.
I wish there was a tag for like starting undergrad versus finishing undergrad.
Yeah, like a first year student probably wouldn't be able to follow this argument, right?
Yeah. There's kind of like a big gap, I feel like, between like first and upperclassmen.
Yeah, that jump in economics is pretty big. I mean, like in my intro economics in the business math course I teach, it's like we teach them the supply and demand curves, but we don't really do much after that. And maybe if they're lucky, they'll see like a parabola and we talk about monopoly, right?
Yeah.
Establish.
Wait, what's bell practice? Floofy, what you talking about? What you talking about, Willis? Oh, Stookie says I have half hour before bell practice.
Oh, bell practice.
Oh.
Ringing a giant bell.
Yeah,
I
I think Suki plays the bells if I remember correctly.
Oh, sick.
Yeah.
Not
Tubular
one singular
bells?
bell. Like
I think Stooky's a bell ringer. Yeah.
Oh,
It's awesome.
tubular.
So tubular. Oh my gosh. Yeah, like percussion bells. Yeah, exactly. I haven't played the bells in band in so long.
Yeah, I just can't. I just can't contribute much to this conversation, to this thing. I wish there was some physical, practical examples, because this is supposed to be applied mathematics, right? So, like, what's the applied? What is it actually going to?
It feels like it should be applied. I agree.
I feel like, okay, maybe this is crazy. Like, it does feel like applied because, like, there's no way someone in pure math would be doing this. That makes sense.
Oh, yeah. No, I totally
Like-
get that bit.
I definitely do not want to see these equations ever again. in my life.
Also, like, realistically, like, the math is not that hard, if that makes any sense. Like, physically itself, like, we're not doing anything crazier than just, like, kind of equations that people would generally see. We're just attributing meaning to those equations in ways which are really esoteric and not understandable from the video.
Yeah, that's. Why do we normalize? I kept wondering through the video why. Why are we doing? Why are we normalizing? Why are?
Because, like, they want to keep the axes, like, from 0 to 1 on every variable, and maybe they don't. Maybe their original definition. I mean, definitions of variables would have been very helpful, I think, in a mathematical, like, critique.
Yeah. So why are we just yeah, I totally get that.
Yeah.
I feel more confused having watched it. Yeah, and I think I'll wrap that up.
Wait, what is this that Stookie is sharing with us?
Picture bells.
Oh, son of a gun.
For like Christmas?
Christmas. For
I
any
mean, they
occasion.
don't have to be at Christmas, but yes.
Yeah. Well, that's what I'd see it from, right? All right. Any other?
Seeing those bells, I'm just picturing like Stookie wearing like really like soft white gloves while playing them.
Could we save our notes too? Like add to wish
Yeah.
list. So like it'll save.
You can edit them after. So if you click vote, like you can go back.
Oh, sick. Okay. Yeah. Then I'd like to move on from that.
This title. Oh my god.
You want to read it?
What? A pseudo-spectral solution to the
The brachistochrone.
brachistochrone. Thank you.
Yeah.
What?
Oh, control problem, bruh. Sorry.
It's aimed at
Man's
students and engineers with a calculus background who want to concrete and optimal control problems. All right.
Okay.
Let me pull it up on a different tab.
I never took a controls course, but you know,
I took robotics,
osmosis.
but never took any sort of control.
The brachystegraph.
Oh, this is gonna be quiet. This is quiet. Sorry, guys, crank that up.
Crank that shit up.
All right, go.
Prone problem is a classic nonlinear optimization problem with a rich history. We won't get into that here, but the statement of the problem is very straightforward. What shaped ramp rolls a ball from the top to the bottom in the least amount of time?
All right, I like that already. It's already giving us a
That's
what
fine.
are we doing?
Yeah. Is it linear or is it one of those like weird like 1/x's? I can't remember. But yes, yeah, it's a cool
Definitely
question.
not linear.
Oh, are you actually not familiar with this one?
No, I don't know it.
Oh, sick.
I
Okay.
remember seeing it on like somebody else in the science community has done this. I think it was like might have been like Minute Physics or something like that.
There's a very popular Vsauce video about it as well.
Mm.
So, that's
Oh, part of a cycloid. Ooh, that's fun.
Ooh,
spoilers.
that's
Spoilers.
In this
Vsauce
video,
did. Oh,
I will
okay.
show
Vsauce,
you how
Michael
an
here.
engineer
Hey,
might solve
Vsauce,
this
Michael
problem using a modern optimization
What is it,
technique.
Christopher?
What
First, what are
engineer?
the parts of an optimal control
That's
problem?
my question.
It has an objective. It's trying to minimize something,
Ooh,
whether along the
hey, that's
path
funny.
or at its terminal condition.
Lagrangian, maybe.
It has boundary conditions at the endpoints that must be set.
Hmm.
The solution is subject to dynamics. It must obey the laws of physics everywhere. We call these equality constraints. There may also be inequality constraints. These are regions where the solution's path may not go. The optimizer also needs a starting place, an initial guess, and while it won't be optimal, it's important that that initial guess satisfies any constraints and boundary conditions. This problem will not require a running objective nor path constraints.
That makes sense.
These parts formulate the problem, and they are fed to the optimizer itself. In this case, IPOPT, Interior Point Optimizer. The optimizer will iterate on its decision vector z, ultimately either converging or failing. If it converges, it will produce an optimal solution, hopefully, optimal states, optimal control, and an optimal final time, which is what we're after. This video will focus on the problem formulation. We will form this problem as a pseudo-spectral optimization.
Wait, so are we
By
just
the
not
end,
talking about the
you'll know what that is.
optimizer at all?
I was gonna say, like, the
Isn't
optimizer,
that how we solve it?
if I remember, it's one of the physics properties, because this is like, you can maximize, you can minimize time using some sort of I forgot what operator it is, but like it's like a Lagrangian or something like that. You're kind of like doing something
Yeah.
to it, right? I think you're on the nose with that.
Yeah. I
But
guess it's just like interesting because I kind of figured, okay, like again, as an engineer, I think instantly numerical analysis, like we're doing solution iteration, we're going to talk about like closeness to solutions and, you know, drift and all that stuff. And like that all would live in like how we're solving the problem, not like how we're setting it up. But I mean, some in how we're setting it up, I guess.
yeah, I guess it's good to know that like we're doing like basically a physics problem. We're just starting with all the initial things, and then we're like, okay, now what? So I'm okay with this whole little bit of setup for those of us that aren't physically inclined. That's not what I meant to say. You know what I meant?
Continue on.
Yeah.
Let's talk about ramps.
Ramp.
All rolls down a ramp. At all points
No,
in
I
time,
drink.
it has an X position, a Y position, and a velocity. These are the states, X, Y, and V. All
No.
points along the ramp also have an angle with the vertical. This is our control, the thing we're going to change to achieve our objective. Additionally, at all times, the ball is subject to the laws of physics, the dynamics as shown here.
Unfortunate.
And you can sanity check these. At theta 0, the ramp is vertical. Sine is 0 and cosine is 1, and these equations become free fall equations. Optimizing this for all times would be a big problem, and we are engineers. We don't solve big problems all at once, we solve a bunch of little problems. So we discretize the curve, we break it up. All the same rules apply.
Okay, so we are doing numerical analysis.
This is what you guys do.
But now we only
This is numerical
care
analysis.
about
I mean,
them
in a way.
at these node points. It's important
Most
to
engineers
understand
would
that
solve this
these
problem by
nodes are not points on a 2D plane.
Like
using
iterating.
someone else's model that already solved the problem.
Each one holds
Oh my
Yeah,
gosh,
that makes
finally
sense.
some linear algebra.
including time
Yeah.
and the local angle with the ramp.
God, this
the
reminds me
control.
of intermediate dynamics.
And there are two very important nodes, the ones on the endpoints, the boundary conditions.
Those ones don't move.
Because no matter
Sensation.
what solution we come to, those positions are fixed. And the time of the final node, the final time, that's what we want to minimize. Let's revisit the optimal control problem and talk about this optimal control problem. The objective will be to minimize the final time. The boundary conditions are the top and bottom of the ramp. I'll give these positions now and we'll use them later. The initial velocity is 0, the initial time is 0. The final velocity is free to be whatever
Make it a
likes,
little faster.
and so is the final time, even though we want to minimize it. The equality constraints will be the dynamic equations we laid out earlier. This formulation has no path constraints. The initial guess will just be a straight line ramp. It's simple, we know everything about it, and we know it's a valid solution. Let's talk about the operations you might want to perform on a discretized curve. You might need a derivative, and you would use some form of finite differences. You might need to integrate it, and you would use some area rule or a 𝖈𝖗𝖊𝖉𝖎𝖙𝖘 method. If you needed a value between
Oh.
the
This
node
is
points,
just numerical analysis.
Yeah, I was gonna say.
Analysis.
This is actually just breaking down how one would do it.
Yeah.
Yeah, it's just solving a PDE, isn't it? Right?
Yeah. Or
This
like
is
a little system.
this is kind of a nice perspective. I appreciate this because I have not done any like engineering, but like I've done the physics, I've done math. I would understand what this is. Runge cutout. We're gonna code this thing.
To
Okay.
be honest, like I don't think an engineer would be doing this. I don't like.
Well, they
uh,
probably just run it into like an optimization solver, and then like it's already
Yeah.
programmed to do all that stuff anyway.
But
But
I mean, like you just test it physically. I mean, that's usually what you would do if you're building something that you actually want to have the minimum thing. Because I
Getting
mean,
like
We'll
getting
simulate?
flashbacks because I'm pretty sure I built something like this in my undergrad.
yeah,
It's like
Wait, that's awesome.
terrible flashbacks.
that's cool.
you could
Yeah,
interpolate.
memories with this problem
The
audio. Yeah,
shortcoming
totally.
of all these methods is that to improve their accuracy, you need more node points. They don't
Mhm.
scale well.
No way.
Now, to go any further,
We talk about
we need
Who would've
at
thought?
least
bringing.
an
Oh my god, it's literally
appreciation
numerical.
for
It's
Lagrange
crazy.
polynomials.
Lagrange polynomials,
We're
yes.
I
going to
hate
create
numerical.
I love
analysis.
Lagrange. I love
Lagrange
these.
polynomial fit through these
Oh my
5
god.
points.
I don't know
I
what
know
this
these
means right now,
definitions
but sure.
look intimidating,
Yeah.
but I
No,
promise you,
yeah.
this is a wonderful piece of mathematics. For a 5-point fit, we
This is
are
actually
going to
crazy.
generate 5 basis functions. Each basis function is formed from multiplying 4 things together. Then to generate the polynomial, you take each one of those basis functions, weight them by the nodal value itself, and then add them together.
Oh, okay.
Yeah.
Something to note.
There's a really
At
long
each
proof
point,
about why it works.
One weighted basis
Alright,
function
that's kinda cool.
meets that point exactly, while all the others are 0. Equally spaced points are not the most accurate way to generate the Lagrange
God.
polynomial.
Oh, is it
This is
really not
so-
true?
Legendre, Gauss,
Yes,
and Lovato
because you get
figured
ringing
out
on the
which
ends,
points were
so
the
you
Ah.
just space
so
it.
we're going to use those.
Oh my
and
god, bro.
regenerate.
solve it like
Now,
a
if you
numerical
take the
analyst should be the
derivative
title of
of
this
the
video.
definition of the Lagrange polynomial, what you find is that
Yes.
operation
There's the
is
matrix.
expressed
Pretty sick.
exactly as a matrix multiplication.
All right.
Damn, this is hot.
This is cool.
I don't really know why we need to talk about this, but I do think it's cool.
Yeah, it's a little much. I think this is targeted for like an actual student.
If
Then
you take the integral
Yeah,
of the
probably.
definition of the Lagrange polynomial, what you find is that that operation can be expressed exactly as a matrix multiplication.
think they should explain a little bit more about why you can express it as a matrix multiplication.
Oh no, this is engineering, my dude. We're not
I
doing.
mean,
We,
that's
we
true.
don't get
That is-
explanations in engineering.
That is a fair point.
Recall our
actually.
common discrete operator.
Why prove it when
Formulating
we know it
using
works?
Lagrange
You said so yourself.
allows us to
What,
express
you use them to
linear
predict what, 5
correlation
million
with
shark attacks in
polynomial
2027?
evaluation.
Or what?
We
Stop.
replace finite differences
Get out of here.
with simple
And
matrix
graphs.
multiplication. And we
This
replace
isn't Funny Bunny,
linear
okay?
beginning.
Unfortunately, it's not Funny Bunny.
True.
Come on, I need to know the funny
So
bunny
why does
story
our
at some point today.
Dude,
Oh my god.
Yeah,
Okay,
tell it.
Solution
we'll say it after this.
Lagrange basis
We should just
functions
watch it
allows
again.
us to express a continuous path using nodal values alone. It allows us to express our dynamics, a system of differential equations, as simple.
Is
matrix
capital D
multiplication.
matrix the same
While
as
our
capital A
optimal
matrix, or
problem
are they
does not
different?
have a running cost. If it did, that could also be
Probably
expressed with simple
different.
matrix multiplication.
Or maybe
In
it's a
iterative
Franz
one?
thing, I don't know.
𝖈𝖗𝖆𝖆𝖕 expects a smooth nonlinear problem. Smooth in the value, smooth in the first and second derivative, smooth in the Jacobians, and smooth in the Hessians.
Oh,
So how
smooth
Hessians.
Damn, you're
use
smooth
Lagrange
everywhere. This
to
is
We're gonna
dynamically
talk about
constrain
smooth
this
brain
and
time. Let's
constraints of
Uh,
The
splines.
Lagrange
Oh my
basis
god.
functions are defined over normalized time from negative
Ah, we're
1 to
normalizing
1,
things again.
and their derivatives are taken with
Yeah,
respect
that one.
to normalized time.
Yeah.
I
So
don't
we
want
will
things to be
use linear
normal.
We need some
transformation
symmetry.
to move from normalized
Yeah.
time to physical time, and we will use the chain rule on that transformation to move from derivatives with respect to
Yeah, we're
normalized
just
time
setting up
to
the
derivatives
code
with
for all
respect
this
to
stuff
physical
then.
time.
This is like
Yeah.
plug
Now
and
is a
play.
good time to draw an important distinction. Our formulation computes an approximate state derivative. That is not the same thing as the state derivative computed from the system dynamics. We would like them to be very close.
True.
The difference between these two state derivatives is known as the defect, and it is the optimizer's job to drive the defect to 0. When the difference between the Lagrange derivatives and the system dynamics is sufficiently small, that solution is feasible. The solution sufficiently satisfies the system dynamics. Okay, it's about time we start rolling some
That's cool.
balls. But first, we need
What's
to make an
sufficiently
initial
small?
Roll
guess.
some
We
balls,
need
boys.
to fully populate our nodes and our decision vector. with a
Sufficiently small
feasible
is whatever you
solution.
want it to be.
And we're
Aleph.
going to get
Yeah,
there
of course.
by rolling a ball
Yeah, it's
down
just a
the
delta,
road.
right? So, yeah.
Yeah, it's whatever
Now
you
that we have a
your
guess
computer
for
can
the
handle.
final time,
Fair enough.
we're going to use that to place 7 LGL nodes. We
What's an
populate
LGL?
those nodes with the states,
You know.
time, and control the ball had there. We
Make
assemble
jobs
those
smaller.
nodes into a single
My bad.
flat decision vector. This is where the optimizer will start. It is finally time to optimize. As the optimizer runs, we're going to keep track of the iterations and the final time.
Whoa, what? Oh, what is that?
It just dips.
As you may know, the brachistochrone problem has an analytical solution, and that shape is called a cycloid. I've placed the cycloid and its
How'd
final
you know?
time here, and it seems like our solution is an extremely good match. I'm going to rerun the optimization with the cycloid already in place.
I do wonder what optimizer they're using.
There's different kinds.
Yeah, a lot.
Another way to look at this would be to
It also didn't
observe
take them
the
a lot of
states and the
iterations
control
either. It was pretty
throughout
fast.
the optimization.
Yeah.
And I'll place the
That depends on the
cycloid here
optimizer
from the
too.
start.
Wait, what were they showing us?
Yeah, I don't
Oh,
know
they
what
were
that just
showing
did.
us-
The versatility.
Let's go back.
But
What?
okay, I feel like I missed that, but I saw there's like the functions of over time. It's like the XD.
Another way to look at this would be to
Yeah.
observe the states and the control throughout
So
the
they're trying to
optimization.
optimize the
And I'll
states or
place the
whatever, right?
cycloid
Oh,
here from the
interesting.
start.
Oh, okay, I see.
Yeah, I think they're
Oh,
just saying,
okay.
like, rather than optimize the original problem, you can optimize these things, and that should give you the optimal solution.
That would make
I think they're
sense.
just trying to show, yeah, that it gets
I'd
usually
like
the
to
same.
demonstrate the versatility of this technique by changing the problem slightly. Let's continue to minimize time, and additionally constrain the final angle of approach at the end of the ramp.
Oh, okay,
We want the
gotcha.
ball to meet the
That's
end of
dope.
the ramp at a 90-degree angle. I'll place
Like
the
a-
cycloid
like a
here just
cent-
for reference.
Yeah. That's interesting.
Cool.
And once again, we can observe the states. I'll include the cycloid for reference and mark 90 degrees on the theta plot.
Is this what Red Bull does whenever they try to like send a dude on a bicycle down like a giant ramp?
Maybe.
Now, is this solution truly optimal for this problem? The truth is, I don't know. But it looks good.
Do they want that individual to hit the end of the ramp at the 90-degree angle?
Yeah.
That was a good video.
That was nice.
End sentence there? That was fantastic.
Yeah, that's what we say.
Good enough is good.
It's good.
Close enough is good enough.
Yeah.
I like that. That was pretty well put together.
I like that they changed it like a lot. I think that's cool, especially if there's a video out there that like already kind of explores this problem.
Yeah. And more importantly, like they actually like gave another example and like how that would work, because we got a thing that works now. We got something, and then here's how it solved our first thing, and here's another example of why it works better.
Yeah.
So I can see the power now. I would say this is like 8.5 on my book so far. At least pretty good.
That's a Funny Bunny video for me.
Funny Bunny?
That's like a 8.99 whatever I gave the other one.
Absurd. You want to hear about Funny Bunny now?
Absurd.
I mean, I liked how you're just like roasting it in the beginning. It's a board game.
You should see like the reviews that I wrote for all of my professors. Like, it was
hypercritical, but like at the end it's like, oh yeah, they were pretty cool after all.
Yeah, I'm like, you tried really hard, and I appreciate that. That sounds really backhanded, but like, I meant it.
Pen, any notes?
Young engineers cook everything on high. Floofy says. No, I think you guys captured kind of the idea. I think I would definitely put this on the other side of about the same. I don't know if I'd go like into outstanding personally, but I'm fine if you want to put it up there.
Well, I enjoyed it because like as a math guy, like you can throw all this math at me, and then as long as I understand the philosophy, and now I understand what our problem solving is, and the extent of like how to do it. Because another thing I want to do is like get into more engineering stuff. So this is exactly right up my alley. So, and then
what was his intended audience? Was it undergrad, grad?
It said
Probably
students and
undergrad.
engineers with calculus background.
Undergrad, grad, yeah.
Yeah. So
I will say, as someone who took a numerical analysis class, this video was like it was able to say so much of the stuff that like we use and we think about, but like in an infinitely more digestible way than how people normally talk about it. So that was cool.
Something really. Yeah, good. I think good hook. The visuals were phenomenal. Has a very good grasp, I think, of Manon.
yeah, I appreciate all the other like the polynomials getting drawn, because I could see like they're there, and that's the whole point of having them drawn, means that they're going to be used for something, and in this case they all add up at the end. So
Yeah. Like I could feel the polynomials. I could feel the ramps. I could see the spherical cow being dropped down the ramp. It was fantastic.
do you guys know any more about that interior point optimizer thing?
I mean, I know about like, I basically learned like really shitty optimization techniques, because those were the ones that are like easy to code, but like you can do crazy things. So I don't know what like it does, but it probably, if you know like Euler approximation, that's like one of the easiest like techniques for solving some of that stuff. So that's sometimes how it's done.
Yeah,
Okay.
Run the code is usually like a multi-dimensional
Yeah.
solution, I think, that's similar to Euler.
Yeah, it like changes the step size like based off of the
Yeah.
fucking weighting stuff, and is smart instead of like,
Yeah.
oh, let's make it really tiny and move only a little and then blow up our computers.
Oh yeah, a small delta. I did that for fluid dynamics, and boy, we got some wacky Reynolds numbers out of that.
Oh yeah,
And then they broke.
I had labs on that.
That was I did an internship, and so like half the time was just me running it for like 12 hours, and it'd crash and nothing would get saved.
That's so
That's
fucked up.
It was an easy internship. It was really funny.
I'm waiting for it to compile.
Let's see. I want to say good things about this. I don't want to. I'm gonna have to come back to this though. I think this is like quite nice. I want to articulate this better.
My only critique would be like I think that the matrix multiplication thing was like a little.
Yeah. Why do
Like-
we need that?
We didn't really need that. Although it was cool. And yeah, I think that was the only part that like wasn't really explained. It just kind of said it.
Oh damn! GitHub repo is 500 plus files. A badass optimizer.
Oh wow.
That is crazy. That's a lot.
That is nuts. Yeah.
Wonder what happens when we would take one of those away. Okay, I'm gonna make time. I'll make a note to get back to this. I do want to say this better, but I'd say, I could be at swayed. I'd say like an 8 then. 8's pretty good.
It's pretty good.
Yeah.
Like I would watch that video.
Very,
and I would enjoy
very
it.
good video.
Very concise too. I feel like I learned like the first 3 weeks of a engineering course in like 13 minutes.
You're never gonna learn that in engineering, but yeah.
Or what is this then?
I mean, a numerical
It's
analysis is like
numerical methods. Like it's a multi-dimensional numerical methods course is kind of what he's introducing us to here.
Yeah. Okay.
Like I don't even know what you would call it. Like I feel like just analysts. Like you would be a math major, but you would do like applied math, and you would be like an analyst of some kind. I feel like.
Yeah. Let me just make the quick notes then. Learned something new. Numerical methods is useful. It's sick as heck, you know. Very cool. I'll come back to that.
Cool.
I like the examples. Or it didn't also treat me like I was stupid. I think I appreciate that. Like he actually explained the what we're doing and what does it do.
But also like just explained it in a super approachable way.
Yeah.
Right. Like I don't feel like it ever got it. Like maybe it was over our heads slightly, but it never felt like it was unobtainable if I watched it a second time.
Yeah. I think the focus on ideas was good. Like there was a lot of math stuff in there if you could sink your teeth into it, but it wasn't like a barrier, you know.
Showed the solution.
I agree with you, although as much as I like to see those matrices, I don't know if we really needed to have that section of the.
I think it's hard because doing this problem and not talking about the optimizer, like doing the differentiation stuff and the integration in general, like that's going to be more related to the optimizer than setting up the problem. Because to be honest, like the first half of the video, like we could have stopped there because he answered like how we set up the problem. You know?
Yeah. I agree with you. And then he just kind of was like, okay, now we're just going to stuff it into the optimizer and let it do its thing, right?
Yeah.
Yeah, I kind of wish I knew more about that, but that would probably be. Does it really help us?
I think like low-key he just ended up kind of talking about the optimization without talking about it, which I think he could have gone just a little bit farther just to say like this is how the optimizer kind of like does its iterations and like these are the values that like it needs. Because talking about that the feasibility like of a solution with the difference between the defect or whatever, like that's definitely in the optimizer.
Yes.
Yeah, that's true. Okay, I'll come back to this, but I'm gonna leave these notes here for now. I enjoyed that. I really enjoyed that. Okay, let's hit another one.
Oh no, Galois.
Galois
Wait,
theory.
didn't we watch this one already?
Oh, have we?
Did we? I haven't.
I feel like I watched this with Stuki.
Okay, then we can crank it up because I understand the gist of Galois theory, and modular stuff, probably.
Wow, undergrad? I mean, I guess like late undergrad.
That's awfully generous.
The Galois fields in undergrad.
Dude, that is maybe fucked. Like, I don't know.
Crazy. Yeah. Math enthusiasts are familiar with modular. Okay, well, yeah, I guess it's probably just going to be the basics of it, do you think? Yeah.
Maybe?
Should be, because...
How long is it? Okay, it's not super long.
Okay,
let me...
Slide. I'll crank up the speed on this one, because I don't suspect it being
Time
actually...
to go on mute, Stuki. It's your favorite.
Have fun,
Favorite
Stooky.
background music happening right now.
Oh,
Piano.
no.
Wait, what's up with that?
I feel like Stooky got triggered most by the music.
No, really? That's so funny. It's giving like Mensa.
Feel very zen right now.
Here's one you've probably heard before. Can you do arithmetic on a clock? Can you
Never
add,
heard that.
subtract, multiply, and divide when you're not allowed to use any numbers larger than 12 because it just loops around? This is called modular arithmetic, and you can find explainers about
That's
it
a
all
funny
over the
showing.
place, and it's mostly pretty
1
simple.
plus 1 equals 0.
Although, first of all, you don't use the
True.
numbers 1 through 12, you use 0 through 11.
I'll crank it
But
up.
after that, the
You
arithmetic is
can
just
use
walking
1
around
through
the
12
clock.
if you want. I'm not
You
going to
can
stop
add,
you.
walking
Yeah,
forwards,
true.
and if you go past
You
11,
can do whatever you
just
want
loop
forever.
back around to 0.
The piano has to
You
be
can
it.
subtract, walking backwards, and if you go past 0, you loop back to 11. You can multiply, that's just repeated addition, it works the same way.
Alright, I'm familiar with cycles. And group theory. Let's get to it.
Mod.
But can you
Modular
divide? Division is repeated subtraction. You have to subtract until
Field.
you reach 0, and that's a problem. Let's try 8 divided by 3. We start at 8 and repeatedly subtract 3 until we get to 0, and we can't do it. It just loops around through 5, 2, 11, and 8 again.
Well, we have to hit
Well,
0?
let's try
That
another way.
because 12 is divisible
Division
by
is the
3.
inverse of
Damn.
multiplication. So if we want to divide 8 by 3, we need to ask what number times 3 equals 8.
Hi, DZ. How's it going?
There's only 12 numbers on the clock, so we can just list all the multiples of 3, and none of them work. You can only get 0, 3, 6, and 9. And it's easy to see why. 12 is divisible by 3, so if you keep adding 3, you keep looping back to 0 after 4 additions, and you can't hit all the numbers.
No way.
You can add, subtract, and multiply, but you cannot divide numbers on the clock. Of course, you can't always divide in the integers either. If you divide 8 by 3 there, it's 2 2/3. It's not an integer. You have to use rationals. But there are other forms of modular arithmetic where you can. Let's try the integers mod 11. Now there are only 11 numbers on the clock, 0 through 10. Addition, subtraction, and multiplication all work the same here. What about division? Let's try 8 divided by 3 again. If we repeatedly subtract 3 from 8 on this clock, we get 10.
Whoa! The piano
Let's
music
try
got
that.
was crazy.
Isn't that...
3 equals x.
It's presentation. It's kind of nice.
List the multiples of
What
3
do you
mod
say, Max?
11.
So field
and there
over
it is
p
again,
to the n,
10.
prime to the n is like
You can
f
try
of
this
x
for
mod
any division
something
mod
like
11,
that. Yeah.
and you'll still get a valid answer. You can divide on this clock without needing to use fractions. A mathematical structure like this, where you can add, subtract, multiply, and divide, is called a field.
What?
The real numbers and the rational
Is
numbers
that
Why are we
are
getting
fields.
Wikipedia page for
The
field?
integers are not fields because you can't divide
I
them
thought-
without
Crazy.
bringing
It
in
would have been
fractions.
funny to just a field.
The integers mod 12 are also
Yeah.
not a field,
Wait, that'd be
but the
cute.
integers mod 11 are. It turns out that modular arithmetic
'Cause they're
forms a
prime numbers,
field
right?
if and only if the modulus is a
That has to
prime
be a
number.
prime number. Yeah.
Yeah.
Mod 2
Prime
works.
number
mod 3
guarantees
works.
that you have
Mod 4
multiplicative
doesn't.
inverses for
3
everything.
divided by 2 has no solution.
Right.
Mod 5 works, and so on. A field with a finite number of elements like this is unsurprisingly called a finite field.
What?
But it also has another name, a Galois field.
Oh, is it
A lot of
actually?
explanations end here, at least if they're not specifically about finite fields. But this isn't the
wild.
full story, because in 1830, the mathematician Évariste Galois figured out how to build fields with a composite number of elements. Hence the name Galois fields. Let's
Yeah, is that
take the
how it works?
integers mod 9.
It's no zero
Mod
dividers
9
in the
has the
field.
same problem as mod 12. If you try to
Other than
divide 8
0?
by 3, there's no solution because 9 is divisible by 3 and it just keeps looping. What Galois did, well, he did it in a very different way, but one way to think about what Galois did is instead of one clock with 9 numbers on it, you can have 2 clocks with 3 numbers side by side. And the order of the clocks does matter, so you can write 9 numbers on the pair of them.
Oh, the counters.
Now, these look like they could be 2-digit numbers in base 3,
Is this
if you
just
ignore
base
the leading
3?
zeros, but they're not.
Yeah, I was about to say.
Each clock
Oh,
is
they're not.
independent of
Was
the
this
other.
where that
Addition
composition
and
stuff
subtraction
comes from?
are mod
What's
3 on
happening
each clock separately with no carries.
Okay, I
Oh,
can take
no
that.
carries. Oh, that's interesting.
You can
Oh,
write
I
them
see, I
as
see.
numbers. You can even convert them to base 10 if you want. but addition and subtraction don't work the same as in base 10 or even in mod
That's
9.
weird. Why do we write them like a full number
If you
then?
write out the addition
Not like a
tables,
pair.
not multiplication tables,
Tuple.
for mod 9 versus this, which I'm going to call mod 3x3, they're different. Now, this mod 3x3 addition
It's
works
not
perfectly.
standard,
Whoa,
okay.
whoa, 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 whoa! What is
Every
going
possible
on with this
addition and
mod 3x3? What does this take? What? I'm overwhelmed with data right now.
So he said
and-
that. Oh, you want to go for it?
No. I just said
So I'm okay with the plus mod 9 because that's just regular mod 9.
Right. Because you have the cycles, you have repeating patterns in mod 9. You can't actually get to the zeros. You can't get to the any of the other numbers in mod 9. So describing it instead as the 3x3, you can then reach it, and that's like kind of like a field. I'm guessing is what the goal is to do, but it acts differently. It just fundamentally acts differently.
I don't know why they wrote them as like 1, 2, 3, 4, 5, 6, 7, 8, but that's like writing the base 10 version of the mod 3x3. So you would have to convert it into the mod 3x3 like notation, then do the addition, and then bring it back. And that's how you get the numbers on the right.
Actually, yeah, that's a good point. What?
Which is like, why did they
Right,
do
like
that?
I'm
Why
so
didn't
confused with this chart. Like,
Should have
they
drawn it
should've
like a
just,
Sudoku.
written it-
Yeah.
They should have written it in mod 3x3, bro. Like, what the heck?
Yeah. If
yeah,
they,
like look at the one row. It's like 1, 2, 0, 4, 5, 3, 7, 8, 6. How the fuck do I get those
Yeah.
numbers?
I don't really know how the addition. I
I-
wish they like went back and like did like an example of like they're like, oh, you just add and you don't carry. But I'm like, how?
Yeah, I feel like
Yeah.
that went by very fast.
I think, yeah, that a little too quick. If they like showed the 3x3 chart and then converted it back, then we can see
Yeah.
the discrepancies. Then I think that'd be a little clearer. Unless that does it like literally right now. Let's find out. But I'm,
So,
I'm okay.
but also I think like what
You can
they're
check
doing
that for
is they're
yourself.
taking the original one and the zeros are kind of moving around a little bit somehow, right? So are we just getting a permutation of like the row? Is the row just moving?
Yeah,
Like,
it
if
looks
I look
like
at the row of 1, all of the numbers are there. It's just getting moved around a little bit, right? The row for 2.
You can't see them.
Okay,
Okay.
so we're just getting permutations of rows basically.
I think
Some
it's
rows are
just,
staying
like-
the same though, which is interesting. The 0 row is the same. The 3 row is the same.
That should be the same
Yeah.
for the first bit, right? Oh no.
because it's probably like the ones which are the divisible in the same base, right?
So
it's
the
3,
0
6, and then,
divisors have no change to the rows.
like,
Hmm.
yeah.
Yeah, okay, that makes sense. 6
And
so
then it
6 is the same too. Yeah, okay. So the 0 divisors have no
3s?
change, but the other ones get rotated around somehow.
And like the zeros replace like the. Oh no, they don't.
Yeah, there's some
The
sort of
3s,
polynomial.
like and
stuff.
6s get replaced by zeros, low key. It's weird. It might just be like a pattern that exists, and then like we're looking for patterns in the normal numbers, but like it makes more sense if you look at it in the mod 3x3 language.
But a quick
Yeah.
way is to see that every
But-
digit appears in every row and column. It's
Sudoku.
like Sudoku without the 3x3 boxes.
Ah.
And that means addition and
Hey.
subtraction still work in this structure.
Ah.
Hey.
Now, what
Ah.
about multiplication and division? If addition and subtraction work by treating the two clocks separately, do multiplication and division work too? Let's write out the multiplication table where we treat the two clocks as
here we go,
independent
okay.
from each other.
Okay, yeah. All right.
If we
This is
convert
what I
this to
wanted
base
to see,
10
okay,
just to make it
cool.
easier to read,
Let's divide a
we'll see
clock.
that multiplication still
No.
won't work.
They got it so
The
right the
multiples of
first
3
time.
are
Why did we
still
change
only
it?
0, 3, and 6. Now remember, these aren't actually numbers. What this is really saying is that the multiples of 1, 0 are 0, 0, 1, 0, and 2, 0. But the important thing is that there are still combinations of numbers that don't have a solution for division. One problem we have here is that a 0 in either digit zeroes out that digit. And a 0 in both digits, like 1, 0 times 0, 1, just multiplies to 0. And that shouldn't happen. In a field, for division to work, the product of two non-zero numbers has to be non-zero. How can we fix this? Mod 9 didn't work, Mod 3x3 didn't work, but maybe there's some other mathematical structure where the multiplication does work. What Galois did is to turn these pairs of numbers into polynomials, with the 1's place being 1's and the 3's place being multiplied by x. So now they look like this. If x were 3, then you could do the arithmetic and this would just be base 3. But as it is, it's not base 3, it's effectively base x. Why is
Bruh.
that important? It's important because you can't carry from the 1's place to the x place, because x isn't a number, it's a variable. So it preserves the mod 3x3 structure. but you can multiply 1 by x, so you're not stuck with 0 like you would be if you multiplied digit-wise. So how do you write the multiplication table with this? Just a couple steps. First, multiply the polynomials. But remember, we're still in mod 3, and you still can't carry afterwards. You need to multiply the polynomials term-wise mod 3. Now we have another problem. A lot of these products have an x squared term, and that doesn't work. We'd need to add a third digit to write it. What do we do with it? We can't just drop it, call it mod x squared. That would give the same result as mod 9, where some of the products are 0 when they shouldn't be. Galois's solution was to reduce the polynomials by mod something else, and it had to be something that would never return 0 for a multiplication of non-zero polynomials. We need an irreducible polynomial that is never a product of lower degree polynomials mod 3, because if it were, that product would reduce to 0. The polynomial x squared plus 1 has no roots in mod 3. You can check it by plugging in 0, 1, and 2, and seeing that none of them return 0. Thus, we can reduce our multiplication table mod x squared plus 1. That means doing long division of polynomials, which is a scary prospect. But there's a shortcut. We are not dealing with any products with a degree higher than 2. And in mod 3, x squared plus 1 is the same thing as x squared minus 2.
Factorization domains?
Then we have to see that x squared mod x squared minus 2 is just 2. So we don't have to do the long division. Just look at the multiplication table and replace every x squared with a 2, and then reduce it term-wise mod 3. That gives us a multiplication table where every number appears in every row and column, except for the zeros, and that means division works. This is a field with 9 elements. Would this work for any number of elements? Could you construct a field of 10 elements by making the first term mod 2 and the second term mod 5? No. You can check for yourself, but if you try to build a multiplication table for it the same way as before, it doesn't work.
Okay.
Galois showed that using this procedure, you can construct
feel
one
like
and
there
only
needs to be a
one
little bit
finite
more in here.
field.
There's something
Exactly.
interesting, but I can't quite put my
Prime
finger
power
on what he's trying to get at.
I get it, but it's like it's kind of just like a lot of computation, which I think is not super like intuitive, I guess. Like it shows how you can construct it, but it's kind of like, well, what if we did this? Oh wow, it turns out that worked.
I can see this. I'm familiar a little bit with this. I guess it was just trying to figure out what, like, that x squared plus 1. That's your is that like your divisor space or something like that? Is that like your inverse? No. It was trying to get all the terms, so when you multiplied them, you modded by x squared plus 1, right?
Yeah, and what, like, I want to know, like, what makes x squared plus 1 important? And I think they said something along the lines of it has no prime factors.
Well, we would need a third number. Like, was there reasoning if we wanted x squared, because we're kind of using like a base system, and like our 1 and our x are two different ones, and we'd have to add a third number to write everything, was why they said we couldn't have x squared.
Right, we couldn't have x squared in the products, so we needed to reduce it. But why'd they pick x squared plus 1? That was my question.
X squared because it gets rid of all the square terms, and anything that would go over it. So you can multiply and then reduce the squares. And then the 1 because you still would preserve, like, the multiplicative identity, right?
Oh, so the 1 isn't, like, I couldn't use, like, x squared plus 3.
Yeah, no, because that would be operating. So it's reducible or something like that.
Okay, so Max says it's irreducible mod 3.
Yeah.
Oh, that's the key. Okay, so it has to be an irreducible polynomial mod 3 with degree 2. Okay, got it.
This is why finite fields are also called Galois fields, and they're written as GF of Q, where Q is a prime power. Let's try a more complex example to see this idea in action.
GF is 67.
GF 64 is the field of 64 elements, which is of course 2 to the 6th. To represent this, instead of 2 clocks with 3 numbers on them, we need 6 clocks with 2 numbers on them.
Handcraft.
You can write the elements of this field as binary strings of 6 bits. Or you can convert them to base 10, or base 64, or anything else you want.
How many pens
and in
mod
some ways
3?
that's easier to deal with. But remember, these are not numbers. they're more accurately represented by polynomials of degree 5 mod 2. Looking at the bit string representation, addition and subtraction work bitwise mod 2, which is just bitwise XOR. And this shows us a very handy feature of power of 2 fields in particular. Addition and subtraction are exactly the same. 1 minus 1 is 0 mod 2, and 1 plus 1 is also 0 mod 2. So addition and subtraction give the same result. Multiplication is harder. We use the same procedure as before, but because the elements are 6 bits long,
Oh, wow.
we need an irreducible polynomial of degree 6 over mod 2. There are several of these, but the simplest is x to the 6th plus x plus 1. Now we just do the multiplications and... oh, that looks a little unwieldy. But there's another shortcut that's easier in power of 2 fields.
Oh my gosh.
Multiplication by 2 is just a bit shift. This is where the binary strings are really helpful. All you have to do is add a 0 on the end. And remember, this is modulo our polynomial x to the 6th plus x plus 1, which we can also represent as a 7-bit string. We can do the same trick here as before. Wherever you see an x to the 6th, replace it with x plus 1, because that's the same as minus x minus 1 mod 2. In a bit string, that means you just have to knock off the leading bit and flip the last 2 bits. These still aren't the numbers that we're familiar with, it's just bit twiddling, but this is how computers will do it. We can do long multiplication of 2 numbers
really great
by taking
term.
the first number and
That's
applying
kinda cool.
5 bit shifts to it to get
It
each
is.
power of 2 that could be in the product, and reduce
Me
its
as I
leading.
twiddle my bits.
The swap to like bit is not motivated. But,
Once you have the 5 multiples of powers of 2 plus the original, add up the strings corresponding to the ones in the second number. And again, addition is bitwise XOR. An odd number of ones is 1, and an even number of ones is 0. You can fill in the entire multiplication table this way. One way to simplify it is to compute a list of powers of 2 first. And if you do that, then every number will appear in every row and column, and we have a finite field. This
Wow.
procedure works for any prime power, although the powers of 2 are much simpler. Finite fields, and especially power of 2 fields, have a
here you
number of
go,
useful
WW.
applications,
Yep.
particularly in
Encryption.
computer science, where they are the foundation for many encryption schemes and error-correcting codes. But that will be a subject for another video. Thanks for
Yeah.
watching.
Going ham back there.
Oh, we can stop the video immediately.
oh my god,
Oh my
yeah.
god.
That's
Did
cool.
they talk about how to choose like the base, like the number of clocks? They were like, oh, it's 9, so we'll just like choose 2 clocks with 3 on each. And then they're like, oh, well, it's 64, so let's just choose like 6 clocks with 2 on each. Like, what?
No,
Did
I
they
don't.
ever say why?
Other than the first
the
one.
prime power motivation, I don't think ever got discussed
Ah.
there.
I see.
Until the end. Until the end.
It must be a theorem that like every prime number field, whatever there's a finite. Everything is a finite. No, he said every prime number of something elements can be a field, right? But I was curious why
like
they
the-
use 64 though. Like what? That's not prime.
It's a
64 bits.
it's a prime power of 2. So they're saying that you can always make a Galois field of any prime power. Is what they were saying.
Oh, prime power. Gotcha. Okay,
Oh,
I stand corrected.
see.
Well, then that's
So we
Yes, someone mentioned it in chat. I just can't remember who said if it was WW or Max.
I see. So we just say, oh well, we start with the 2 to the 6th, and then just so happens, we get the
I kind of like the actual example after that too. That was very intriguing. Because it ties into discrete math and encryption and stuff like that. That's kind of cool. And I actually wouldn't have thought that. I would think
I just
polynomials and
thought
stuff
that-
don't.
Max, I just thought that the music was just like really loud. I just needed it to be not as like in my face.
it was just like really intense. Like
Uh,
they're trying to do like the brilliant sponsors.
Yeah, this seems like a very like tried and true channel. Yeah, they must have a bunch of like videos like this. So like between the gap of like okay, and then we're gonna do this, and then like the music goes up and then goes back down. I like that.
yeah.
Such a funny edit at fast pace. But I think I learned more. I would say
Eight.
about an 8. I'm actually a little more,
I don't
8.5.
know. I feel like did I really learn about like personally like I know a little bit about like Galois groups because one of my friends was super into them, which is a funny sentence to say. But but like I feel like this was kind of a like a safari, tour of these objects, and I kind of would have just appreciated one that was like digging more into like how they work instead of just like, oh, let's try to go through like all of the examples. I don't know. Like it felt like the setup was a little less than I would have liked.
Oh, fair enough. Yeah, like why are we doing this? Or the extent of it.
Not even necessarily like why are we doing this, but it's like what are we like why are these interesting? Like what kind of behaviors like might they have? Like I know obviously like it's a field, but like it kind of just feels like, hey, we're doing some stuff and like we're just asking. Like even just the motivation for like splitting them up into like the multiple clocks was I was kind of like, oh well, I mean I guess we could do that. Not really sure why that is the intuitive thing to do.
Yeah, it was missing some of the why or some of the motivational aspects. I
Yeah.
think from my perspective.
I can see that.
I think if you already knew about them a little bit, or if you were more familiar with like Galois theory or something, like I think it would be kind of a fun thought experiment because you might be able to like engage with it a little more.
Yeah, I guess
But
that's
I also
true.
I don't think the motivation of being like, oh, so we all know mod arithmetic.
Yeah.
And right, like that just felt like a weird motivation to me, where it's like, oh, everybody knows mod arithmetic, and here's why you can't, divide on a clock. And then it was like,
Yeah.
okay, and then there were these polynomials, and I was like, oh my god, where did everything come from?
Like
Oh, true.
what I was initially interested, because I know again, Galois groups are not the same as Galois fields, but like there was an interesting conversation to be had about like how they relate to other objects in abstract algebra, and like that's why like my friend was so interested in them, right? So but this was very much just like, well, this thing exists, I hope you like clocks for a 15-minute video.
Yeah, and I think like Adip says it right, like like a bit more of like the motivation maybe in the cryptography realm would have been interesting. Like
Yeah, maybe if it started off like how would we encrypt something? It just to put that in the air and then get into like the clocks. I don't know. I feel like the clocks were just fine. That starts off okay.
Yeah, I think it's just that your motivating question is like, well, you've clearly thought about doing algebra on a clock, and it's like, okay, no, I don't think that's
not every undergraduate has thought about doing algebra on a clock.
No one has thought about this like normally. Maybe you would say like, how do we do algebra on a field or something like that? Like how do we actually construct these? Is there limitations to fields? But like, and I think the clocks are great like throughout the video as like a visual metaphor, especially. But it's a pretty crazy question to go like, so you want to know how to divide on a clock? Like, I don't think people ask that.
Actually, no. I actually do not want to know how to divide on a clock.
I've never thought about it.
Yeah.
Keeping me up at night, bro.
Yeah, just divide the numbers.
Everyone knows x squared plus 1. Yeah. Everyone knows that.
Just mod x squared plus 1.
Don't worry. I think it was serviceable for an undergrad. I think this is like a video one would share to an undergrad to hype them up about like Galois theory, or get them in the idea of it. Because
I think a late undergrad, I would say yes, but this is pushing the envelope.
Yeah.
I think there's a lot of computer science in here that I think a math undergraduate would find
a
little overwhelming. I mean, like I feel like between the three of us, we know how to do bit shifts and XORs and all that business, right? Because we've suffered through that already.
Yeah.
But that's probably where it lost me a little bit, was like when it really started like going into those intense calculations, and it's like, oh, just XOR all this stuff, and I'm like, oh my god.
Yeah.
Kind of like, I feel like it would turn people off if you're a math person and like the whole motivation is just for CS. Not that like it would turn every math person off, but it's if we just go psych, we're just doing it for CS. Like
I did kind of feel that. I'm not gonna lie, because I'm like, oh wow, this is cool. This is amazing. I like this. I wonder what it's useful for. Oh, encryption. Oh,
yeah,
real stuff.
As soon as they went into, as soon as they went into like 2 to the 6 or whatever it was, you're like, okay, they're just doing some crazy encryption shit.
Yeah.
I mean, to be fair, the actual like study of Galois, like the theory goes pretty far.
Oh,
and
yeah.
didn't they do like the Fermat last theorem on this with this set as well or
Yeah.
something like that?
There's some cool math shit, but I feel like it was
That wasn't the hype.
I don't know. It's like the rug pull, you know? Like
I could see that. I think it introduces it kind of well. So if you know at least your groups in basic algebra, basic abstract algebra, excuse me, then you kind of get into like what is this useful for? How can we solve this quote unquote problem? And it kind of does explain it kind of well. I through and through, I think it was perfectly fine for a video. I think it was pretty good.
yeah, I think if I were to like compare it to a textbook that was going through this, it would be a better explanation than textbook, but it also didn't really fill the niche for me as a oh my gosh, I'm a math undergrad, like I want to go watch some cool math videos like explaining, some topic to get me excited about it. It felt like it was kind of caught in between the two.
Yeah, and then tying it with encryption, that's not my hype.
Yeah. Yeah.
That but at least there's a real example of it. But there's got to be something else that was cool.
I didn't mind the last example. I just thought it was very computationally heavy and very fast. So like I think if they would have went, if they would have done like 8 bits or something like that, or like
yeah,
like a block of 4 or a block of 3,
a
2 to 3, right?
a bit,
easier
a
to
nibble.
follow.
Yeah. I also just think like, I mean, if you're gonna talk about encryption, like I think you should give more context about like how it's used, because to me it was just like, well, we're just changing random numbers and doing random things, and I don't know how that would be used for encryption. Like
No, and you know what? They're using 64 bits because that makes up a lot of encryption. Oh, okay, that makes a lot more sense why they chose 64 to me now.
Yeah.
Because everything comes in blocks of what is it, 8 or whatever, right? It is, or
yeah, but like they should really put that in there if they're gonna make, I guess, like maybe that's not the point of the video, but it feels like either it's kind of out of the main plot line if that's not the main point of the video, or like it should be more throughout,
Yeah, who's hyped about encryption? Am I right? I don't care about it.
It is a math thing, that people like for like number type stuff. That's
it's a nice application of number theory.
Yeah.
Yeah, I
like,
guess.
When people say number theory, I mostly think like, oh well, you can do encryption. I don't really know too much else.
I mean, the first thing I actually think about, Damie, is how do I divide on the clock?
True. The question I ask myself every morning I get up and I say, I need to know.
Yeah.
8
wish I knew
a.m.
the answer to this question.
divided by 3 p.m.
Hmm.
When you gotta pick up your kid at 5 p.m. divided by 7 p.m. It's like, what?
To be fair, I did like that visual where it's like, oh, you just keep subtracting until you land on 0, but oh, sometimes you can't, and oh, sometimes you can. Like, I think that's actually a really brilliant way to talk about division.
It feels weird to talk about division like that in terms of fields, though, for what I've seen fields in.
Oh, yeah?
But I think
that's the definition
of... Well, yeah, but like when I think about it, I'm thinking in terms of like the physicality of like, I don't know, inverse of, multiplication and stuff like that, right? So
yeah, but I guess that's all you do in like mod arithmetic, right? It's like if you find the multiplicative inverse of something, you're really just multiplying 2 numbers together. It's really kind of like an LCM thing, isn't it? Right? Like where like eventually when you subtract the mod, you'll get to 0.
Yeah. I guess like the modular arithmetic is doing like so much heavy lifting in terms of just like assuming that people are like ready to be in that headspace, because like, I don't know, circular stuff and like cyclical stuff is like, because I'm not a mod arithmetic guy. Like I know of it, but it's not where my mind goes instantly when I think about fields. So
I could say that on my end, I I love modular arithmetic. I love discrete mathematics.
Oh, there you
So the bit stuff wasn't the worst, but I'm actually not a fan of like number theory stuff by itself. You know, so I'm like mod stuff like as it is kind of cool when it gets to groups, but by itself I'm like eh. So
Yeah.
I actually don't think about dividing time. You're right.
I don't think anyone
Yeah.
does, unfortunately.
Yeah, but I think if they emphasize the primeness a bit more, I feel like that would have been kind of interesting because that
Helpful, yeah.
people aren't as
I
familiar
agree.
with just oh, why does it cycle? Because it's prime. Okay, well, why is it? Why does that matter? You know, and then
Yeah.
you can use that to find, I don't know, the extent you can find crazy prime numbers with it too. It's like
Mhm.
there's
Yeah, or like
a ton of
maybe it was
different
in there, but it
directions.
got glossed over, right? Because I know they talked about like 9, and they talked about how 9 doesn't work, and then they made these like the 3x3 clocks, and I can't remember if that worked or didn't work or like.
No, it didn't work. I think
No.
the difficulty is like once you start just because this is like extremely example based, right? It's like let's go through an example, learn a pattern from it, assume that it applies to everything. But like they don't really do enough of like the foundational building of what the patterns you're looking for are. So like for me, I'm like, well, why are we splitting 9 into 3x3? Or like why are we, because that's the primeness that we were missing in the
Yeah.
foundations.
Right.
Let's see. We cover the basics of modern modular arithmetic. I still like this. Yeah, 7.75 I think is fairly okay. Where would you guys rank this yourselves?
That's difficult. I have higher expectations for videos that have like older audiences, and this to me definitely read as like a fairly advanced audience,
Oh, really?
like because like I did an undergrad. I mean, I wasn't a math major, but I took like a fair amount of math classes, and as a person who's like done more of the applied stuff, right? Like I haven't done modular arithmetic, so it's hard because if you're making this kind of niche, like it either has to be like, okay, this is a modular arithmetic like video only, like for that audience, or you kind of have to do more legwork than I think the video did.
Yeah, I think the second that you get into fields, which honestly, like, well, I would say starting with groups first, like cyclic groups and why this works and why it doesn't work was kind of
Yeah.
okay. But once we said dividing, I kind of got disappointed because I'm like, I think introducing groups first would have been interesting. Then you introduce fields. It's like, okay, what other
Yeah.
operators can we do? Why does it matter? But
Yeah, I guess if you've taken a group theory course or a number theory course, you've already done a lot of this introductory mod arithmetic, so they could probably even maybe get away with removing some of that introductory stuff.
Okay, but see, this lives in the same niche as Funny Bunny to me, right? Because
you're funny, buddy.
I
The way
still
that-
need to figure out what Funny Bunny is.
to be fair, it was much less complicated, like cycles stuff that they were doing, but I do think they handled it better because it was very clear like the limitations of their thing. Like they were trying to do a problem that was like appropriate for their target audience, and then this one I felt like, yeah, it could have totally pumped up more in terms of the detail and like the accuracy, like maybe even given some definitions like in a understandable way, because I think the audience could handle it and it would be more helpful.
I gotta jot notes on this. I can't think of sentences. We can introduce fields better. The introduction with polynomials was kind of okay. Or the relevance.
Yeah, I didn't mind that.
As a working.
I didn't mind that, and I didn't mind. I think, yeah, a little bit more around the x squared plus 1 thing would have been slightly nice. Like,
I mean, yeah, my thing in general is I'm personally a big hater of like someone just going, what if we try this thing? And it's some random like random, just the solution to the problem that like
Yeah,
has
it's
no
like where the fuck
motivation.
did that come from?
Oh,
Yeah,
yeah.
like why are we choosing X? Like you could at least try and say like, oh well, we need something that we can't like add the numbers to. Let's put a variable in there. Like that's fair.
That's what some of those epsilon proofs remind me of. It's just like, oh, what if we just use an epsilon that's square root of 2 plus 3 divided by 5? It's like, how'd you get that? Well, in fact, you derived it. I'm like, okay, well, duh.
Yeah.
But this wasn't as crazy to me. But I
No,
can see I can see where that's coming from, though.
It
Like,
wasn't crazy. It
why-
was completely normal. This is something that like every single professor and video does. So I'm on the losing side here.
Over. I'll finish this later. Overall, a good video. You want to explain what Funny Buddy is?
Okay, yes, Funny Bunny. Funny Bunny's beautiful video about like a board game called Funny Bunny, and they were talking about they're talking about like how to fix Funny Bunny. They're talking about how to make the game more interesting because it had this like cyclic behavior of like where holes appear on the game board, which is done by like rotating concentric circles around.
Okay,
So
yeah.
trying to make like cool patterns basically for that, and it was good, and the guy had a wonderful French accent.
I
French accent thing. Yeah, DP says, yeah, like, I mean, I guess instead of using X, you could use I and just make it complex numbers. Yeah, I mean, that would
Where
be
do real
interesting,
numbers
too.
Yeah, you could do whatever you want forever.
Oh,
You could make it like
I
a
do have a
star.
question for both of you, though.
Yes.
Oh yeah.
Time.
I know we're only supposed to go till 4. But
Yes.
do you want to just keep going? And if so, can Oakley just like jump in the call whenever he wants to and just kind of chill out with us?
Oh yeah.
I'm fine with that.
I'm down.
The more the
Yeah,
merrier.
and then that way I can just I'm gonna take maybe a small break before we do the next video, and then that way I'm good to go till 5.
Right now? Yeah.
Yeah, if that works with you guys.
That's
Yeah, I'm
fine.
down.
I can
Okay,
show what Funny Bunny is for a second. We can watch the Funny Bunny video.
I actually
While
also
you're
have to
doing the
step
funny
away.
bunny, I will BRB, and then yeah, Pencrats, if you want to just jump in the VC with us when you're ready. Then
I've heard this video is hard to search.
Okay, I'm before, because I know that also leads down another rabbit hole, if you will. And I'm not gonna go into any digital circus shenanigans right now. But let's see, math video. Let me just go with that and see if we can find it.
It's called like. Nope, it's gonna be impossible. I think Stucky tried to. Apparently,
Really?
they have a non-Unicode character in their YouTube display name, so you can't even search by the.
If only we could describe like what the video had. French person speaking Funny Bunny
No,
math.
we have the link.
Oh wait, really? Oh, where is it?
Yeah, wait, I can get it.
Yeah, share it.
It's gonna take me a sec to scroll.
No worries. That's so funny. Funny Bunny
I'm
was.
gonna remember Funny Bunny like for a long time, so I think the 8.99 was deserved.
All right. All
That's
right.
me.
No, yeah, that's fine. If you send it, send it in. You could put it in the chat or DM me it or something. Or no, just ping it on the server.
Yeah.
I'm gonna grab a quick bite and I'll be also right back as well while I wait for it. Entertain everyone.
Oh my god. I have to hold a chat room. Oh look, there are 2 missing squares. It's like it's all the way up at the top of the reviews because I reviewed it so highly. There are 2 missing squares in Funny Bunny is the name of the. No one can even see this if I. Hold on. This video was so good. If Funny Bunny doesn't win, guys, can everybody vote on Funny Bunny to make it win, please? For me. It's such a cute video. I kind of want to watch it again to like know, because I know what the punchline is. I will say I had Funny Bunny critique, but I love when I get an ad on our own stream. Funny Bunny in chat. Oh my god, the ad break.
Oh yeah, ad break. That's a good idea. We should just roll that and get that out of the way.
I got so scared I was talking over you.
Over me?
Yeah.
Oh no, you're good. You're good.
Okay.
No, I wanted to go to the bathroom and grab a tea.
Yeah, I gotta check in on some stuff. But if you want to look at Funny Bunny, I sent the link in our.
Okay.
Dude, it's really good. I swear. It's a delightful video.
How long is it?
It's kind of a little long. I think it's like maybe 12, maybe a little longer. 16.
That's what Aleph's, I think, pulling it up for us.
Yeah, I got it right now.
Thank you.
Funny Bunny is a board game where several players try to be the first to have a rabbit with the carrot at the top of the hill. It is made up of 26 squares, and to move forward, players can draw movement cards of 1, 2, or 3 squares, and carrot cards, which make the carrot turn and modify the field, making holes appear. Okay, now that you understand the game, did you notice there are 2 missing squares? Okay, let's put aside the rabbits and the players. Because if we want to understand why these squares are missing, we need to understand where the holes come from. When you start a game of Funny Bunny, the board does not have any holes. We will call this our zero state. Then, after an initial carrot card, we turn the carrot and the hole appears.
The sound effects are nice.
1. Then do it again, you're now in state 2. The previous hole has closed and a new one appeared. And you can keep on doing this. New holes will appear and close, and at some point there will be no more holes again. We're back to our zero state. We can verify this by turning the carrot again. The same holes will appear in the exact same order, and after 10 more rotations, we return to our zero state once again. What this means is that our board follows a 10-state cycle, and instead of representing it in a line, we're going to represent it as a 10-point circle. Each state of the board corresponds to one of these points, and by turning the carrot...
I do think it'd be worthwhile if we could ever play these board games or rec games or anything like that. It should be fun to just get together and play them somehow.
Oh my gosh, could you... Okay, we need to find online Funny Bunny, and then the 3 of us are going to get together and play this game.
Yes.
And we're going to talk in French accents and eat baguette.
Funny Bunny. I got a carrot.
One carrot.
We only move forward by 1 square along this cycle, kind of like a 10-hour clock. And now, by pairing each hole to its state, we can find our cycle of dangerous squares. There are 9 of them because our state 0 does not have a hole. So the first thing you're going to do if you want to become a Funny Bunny pro, in addition to seriously raising your ambitions, will be to retain these 9 locations. Because it means that if you're on one of the other 17 squares, you don't risk anything, no matter how many times the carrot is turned. And, okay, let's be real, there's definitely a star there. I mean, almost. It's as if it was missing a square. Okay, where does it come from? To understand it, we're going to have to do a bit of theory to understand what's happening inside the game. We can turn our carrot
This is some game theory.
9 times. And we'll give a name to these actions. Or 1 for turning once, or 4 for turning 4 times.
Funny Bunny theory.
We can also turn it 10 times or do nothing, it's the same thing. But we'll still call this element R0. And these 10 elements, R0 through R9, so rotating the carrot 0 to 9 times, they form what's called a group. Okay, I'm going to say a few things that are a bit obvious, but that's why they're interesting. If I turn the carrot twice, then I turn it 5 times more, in the end, it's exactly as if I had turned the carrot 7 times at once. Crazy, yeah, I know. The idea behind is that R2 plus R5 equals R7. In other words, we can combine together the elements of our group to obtain other elements of the group. If I turn X times, then Y times, it's like turning X plus Y times.
Oh wait, what's going on with this?
Prove it.
And that's our first... property.
We're proving that we have addition under the group. I believe.
Our second property is that there's an element that we will
Yeah,
call
they're not really
neutral,
proving it, they're just kind of saying
because
that you
it
have
does
it,
nothing.
which is like
If I
fair.
do not touch that carrot, it's like I'm spinning it 0
I guess it's
times,
self-explanatory.
and regardless of the state
Yeah.
we were in, it does not change. The
But
main reason to
associativity is
calling
what we
it neutral is that when you combine
Yeah,
it
following
with
this.
other elements of the group in the same process that we just saw, nothing happens. Turning 3 times then turning 0 times is like turning 3 times. It also works the other way. Finally, there's one last very interesting property in our group. Let's leave our baseline in its 0 state, the one where we have no holes. If I turn the carrot 4 times and I ask you to turn the carrot until it lands back on our 0 state, how many times will you turn it? I'm gonna guess you said 6. For the obvious reason that 4 and 6 make 10. And we saw that 10 and 0
Actually, like
were
that they
the
ask
same in
questions during
our
the video
case.
too, even if the questions are like.
And
kind
I
of
could
silly
have given you any number.
9
With
plus
a
10.
simple addition,
Think about
it's
it, too.
easy to find the
Yeah.
result. And going back to our elements R, what we have just described is that for any Rx, there's an Ry such that when you turn Y after X, it falls back to 0, to the neutral element. In other words, there's an element Y that reverses the action of element X. And there you go. We just saw 3 properties. It might seem a bit heavy, but the ideas behind are quite logical given the context of the game. We can combine rotations to get a new one. We have a rotation that does nothing, the one where we turn 0 times, and for each rotation of the carrot, there's a way to undo it. And there you go. Add associativity and you just defined group, which is going to be really useful for what we're going to do. Because now we're going to assume that every time we turn the carrot, we turn it twice instead.
This is where it
We're
lost
going
me.
to call this new card double carrot. And while the simple
Double
carrot
carrot.
card applies
I was just
our
like, why are
elements
we doing
R1
this?
to our
That's
board
mostly
by
my.
advancing
But, like,
one rotation, double carrot card
It's a
applies
question.
R2.
You could say that.
So in state 3, if you draw a double carrot card, you go directly from state 3 to 5 without opening the state 4 holes. We're going
So
to
my guess is
represent
because
this
we're
by
working in
drawing a
base
line.
10, something interesting about 2's, right? Like 2 is a divisor of 10, right? So there's something probably inherently interesting about doing a double carrot. That's my guess.
Oh, that's a good guess. I feel like the 2 doesn't really get explained. Is my only like, or not my only. It's one of the criticisms of the video. Like, it's an interesting thought, but it's kind of just like, well, we're doing that now, I guess.
Yeah, I thought the group introduction was
on
very
our
well,
10
but
point
now I
graph
don't know why we're
between the
doing
states 3 and
carrots.
5. And we can do the same everywhere. What will become very
So he's gonna
interesting,
get us up.
however, is if we decide to remove the simple carrot cards, leaving only the 2 puffs. Now let's imagine we're on state 0.
They like
And
decomp-
after
he,
our
like, does
first
some
double carrot
decomposition
map,
stuff.
we go to state 2, then to state 4, 6, 8, then back to 0. This means
Yeah, that's
that
a-
the
that's a
holes
shape.
associated with states 1, 3, 5, 7, and 9 did not
The one
appear.
with 5 sides.
In fact, these states are not
I'm
reachable
back
by
now, by the
only
way.
doing double rotations from
Yo.
state 0. We always stay on the same state. We always stay on same parity states. On our 10-point graph, what it looks like is that our previous decagon is now 2 separate pentagons.
Yep.
There's one for the
Yes.
even
Yeah, okay.
states and one for the odd states. And we're going to call them the orbits of our elements R2. And since it's
Perfect,
beautiful, we can do it for every element.
Whoa.
I think the funny thing about this video is like, it realistically is not the most
We can see
motivated
that
between
all
the
3
pieces,
has a
but there's
single
something
orbit
very
containing
intriguing
all the
about it
states.
to me
All
that
5
like
has
made it
5
way more
orbits
memorable
of
than
per
anything else I've
state.
watched.
And R0 has 10 orbits of 1 state each. Because, well, if you're on a state, you will not get to any other state if you do not rotate the carrot. And we can notice something nice. The orbits of R1 and R9 are the same. Same thing for 2 and 8, 3 and 7, and 4 and 6. This is due
I've
to the
taught this
fact
before
that
in
the
my
inverse of an
elementary,
element is like
teacher's
turning
class.
the same amount in the other
Hey,
direction.
that's awesome.
So you will visit the same states, but in reverse order. And now we're able to answer our questions from the beginning about the presence of the star and the absence of the 2 squares. If we represent the orbits on the board, we can see that R2 gives 2 pentagons, one on the outer ring and one on the inner ring. But the one on the inner ring is missing a square, which is a shame. So
Square.
let's add it back. And if we now draw the orbit of the action of R1, so the star we had at the beginning, this new square allows us to complete it. Also, by focusing on the inner ring, we can see that there's a decagon formed by the 10 squares, with the holes in each other square.
I think if they like moved
On the
around
outer
pieces of
ring,
this
on
video,
the
it
other
would be like an
hand, the
all-time
holes are
ever
present
video
1
for me.
square out of 3, and
That's
we do
exactly
have
my
all
tattoo
5 of
chat.
them, but we have only 9 non-dangerous squares. And if we place a pentadecagon whose vertices are on those squares, we can see that there's also a missing square here, right next to the previous one. My personal theory is that they removed those 2 squares to make it easier to see where we changed the ring. Great. We finished answering our questions. We are really happy with a lot of beautiful theory and beautiful graphs. But let's be real a minute. We don't want to stop there. Because
Oh, we
right
don't?
now you would not want to play
No,
Funny
why
Bunny
would you
because
want to
it's
stop there?
definitely too
Ultimate
easy of a
Funny Bunny.
game. So let's change that. Let's complete Funny Bunny into the game that it should have been all along.
Shimmy bunny.
Oh god.
Funny Bunny does not have an internal microchip computing the orbits of the actions.
Congratulations,
Crazy,
Sam, on getting
I
your
know.
QED point.
In reality, it consists of 2 boards on top of each other. The first one has 9 holes, where the 9 dangerous squares are, and below there's a rotating plate connected to the carrot that is used to open or close these holes.
The floor is lava.
Squares 1, 2 and 3 are there to give players a breathing space, and the squares that cannot be opened allow for camouflage when the board below does not perfectly align under a square, which would leave it half open, which is not an option. And now we can do something really fun. We can remove the top layer, leaving only the plate of the bottom board. We will represent using 2 needles, and we say a hole is opened when 1 needle is aligned with it. By removing the plate, we have just gone from 10 to 15 holes, and every other turn there are 2 squares opened at once. We can again draw the cycles of the dangerous squares and find a beautiful pattern, but 15 squares out of 25 is not nearly enough. We can do better.
Oh gosh, what's happening?
For that, we have 2 main options.
All of these
Currently,
square
our
circles.
outer ring is composed of 3 pentagons,
Oh, what'd you say? All these
disjoined
squares
by
make a
the
circle.
action of turning 36 degrees. These are 3 orbits. So one possibility would be to add 2 hands, one for each of these orbits, which makes the game extraordinarily difficult, because each turn there are either 2 or 3 squares open at once.
Fits in the square hole.
The other possibility, much more playable and much more beautiful, is to also dephase each needle from the next. So we can go through our 25 squares one at a time. Let's start by going back to our 5 pentagons, 3 on the outer ring and 2 on the inner ring. And let's start by labeling each square accordingly. This will be really helpful when defining our cycles. Let's say a square is numbered ij if it is the jth square of pentagon I. For instance, square 42 is in the 4th pentagon at position 2.
It's not
And
42.
these are the labels of the 5 pentagons.
This is just
And
like
now
six
there's
seven
3
square.
things we need
Yeah.
to define. First, we need to choose a square in each of these pentagons, so in each of these orbits, by which we will start.
I don't think this is
For each of the
Galwa, no.
pentagon, we have 5
Right?
possibilities,
Well, I mean, like,
so we want a
it's
list of
not,
5
but
digits from 1
we
to
got 2
5.
numbers that are
Let's take
put next to
1,
each
1,
other.
1, 1, 1, and so we position our 5 needles on these squares. Then we have to choose how we are going to visit the inside of the pentagons. They will all be visited in the same order because needles are fixed relative to each other. We have 4 possibilities, R1, 2, or 4, and thankfully they all visit the 5 squares. They correspond to the carrot cards used in
It's
the
kind of
deck.
losing me a little bit here. I'm
Let's
not sure
stick
what
with
he's going
R1,
for.
the simple carrot cards.
We want to make Funny
And
Bunny
finally,
impossible
we
to
have
play.
to decide in
Or
which
very
order
hard.
we're going to go from one
We wanna
pentagon to the other.
make a cycle
So
that
a
hits
permutation
all of
from 1 to
the,
5. Let's
uh,
take 1, 2, 3,
points
4, 5 for now.
with like
Which means that
a different
we're
amount of
going to
needles.
start with pentagon 1, then 2, and so on. Combined with the previous list, that means we're going to start with 1, 1, continue with 2, 1, 3, 1, 4, 1, 5, 1, and because we took R1 as an action, we add 1. So after 5, 1, we have 1, 2, 2, 2, 3, 2, 4, 2, and so on. Physically, to achieve this, you just have to shift our hands a certain number of times 1/25th of a turn, because we took R1. We want to start with square 1, 1, so we leave the needle where it is. Then, after one rotation, we want our second needle to be right, so we shift it preemptively by 1/25th to the left. Then, with the same thought process, we shift the third needle twice to the left, and we shift 3 and 4 times the needle 4 and 5. And we can check while turning that they will indeed start with 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, and so on.
Sure.
And that's it. We are done. This is the final form of Funny Bunny, with 25 squares, each one opening once every 25 turns. And all it took was 5 needles and the kind of carrot cards used. And with the 3 parameters we saw, the first square of each pentagon, the order within the pentagons, and the order of the pentagons themselves, we can create a lot of possibilities. For instance, let's only take needles 2 and 4, let's have them start on squares 3 and 1, and under the action of R1, you will find the beginning star. This is our classical Funny Bunny. But in hindsight, this star is not that beautiful. We can do so much better.
That looks ugly.
No.
Wait, is this a Minecraft song?
Yes.
No.
Copyright?
Nah, it's a video game.
Oh, you're right.
You've probably noticed that all our cycles have a 5-turn symmetry when we turn them a fifth of a turn. This comes from the underlying pentagons. But in reality, we've got them all. Every possible 25 cycle that has a 5-turn symmetry can be obtained and mapped to a Funny Bunny board, and it's 3 parameters. What we did is proving this equation, which I'm not going to go into further details, but do notice...
You're like...
Whoa, where did this come from?
I said like this is not relevant. That was fine. I think it's kind of cute that it's like, oh, we just like turned a board around a bunch and like we did this complicated math thing, but like it's more of a flex than anything else.
I mean, that seems like that's the motivation to begin with, wasn't it? Trying to get this thing to work, unless you found something after the fact.
I think it's like a Trojan horse, you know. Like the motivation is to make a Funny Bunny thing that hits all 25, things. But then, psych, we were doing graph theory or whatever.
This is like group theory, right? This
group theory, yeah.
Yeah, this is some sort of group. Psych.
Put it on a Taurus, yes.
Okay, well, hold on. At the very end, he doesn't like cover it too much more. He's just like, "Oh, we basically just did this. Okay, let's move on." Like, what? Why?
I think it's cute.
It's nice.
The big cycles depend on the 3 parameters once again, and we proved it only using
not
drawings.
That's kind of cool, actually.
Well,
Yeah.
really pretty drawings, in fact.
Wow.
And that's it. That's where the star comes from. We now understand why there are 2 squares missing. We even know that one of the 2 missing squares corresponds to the whole of the 0 state. And that's it. I really hope you enjoyed this video. Please forgive the French accent, I'm doing my best here.
I will never forgive
the
the
French
French
accent
accent.
increases the point score, I think, on this video.
Refuses.
I do think like there's things, especially on like a second watch about this video, where I'm like, okay, if you just tweaked like very small things, it would be extremely solid. But that's like the only video that I like felt that way about. That was also like a math video and also like did some, higher level math stuff that was visual. It's my Funny Bunny
Funny Bunny
case.
For sharing that.
Like you said, it was like it was the goat of math videos. I liked it.
I think that's my winner.
I wouldn't say that's like my favoriteest. What about? But I mean, well, to be fair, I'd like this one. This one was nice.
Do we like this one more or the clock one more?
oh, this one instantly. It's
Yeah.
funny. Like even just the fact that it's about Funny Bunny, I think like automatically puts it above the clock one. I'm sorry.
I think the
I
accent.
have to stop you. It's about funny bunny.
True.
Funny bunny.
Funny bunny.
Funny bunny.
Funny bunny.
Awesome.
And we were just literally just for fun. We were just watching that. So
I guess the thing is like because it's a 3 blue 1 brown thing, like in my mind that's like kind of the audience. I mean it's not, but like, you know, it feels like that's kind of some of the target audience for these videos. You know, it's not the same as like if it was a college and it was like lectures and I was like, oh, I want to like find a really good lecture, you know.
yeah, like it should be accessible to tons of other people. Not like the economics one we just started with. What the heck is that?
Oh my gosh, that made me cry a little bit.
Like
it was better than the AI edition article that I read.
I didn't get to see you do that, but I saw you start it. What was that about?
So bad. It was so bad. It was like if you add 9 to a number, it like makes a pattern of when you add 9 to a number.
No way.
It's crazy.
It's like your times tables.
Yeah, basically.
Okay, so what direction are we going right now? Because it is past 4 o'clock. I apologize, but what's the plan?
Are you guys okay to? How long is this one? About 20? So I bet if we like reviewed this one, that's probably gonna push me about to kind of where I would need to sign off. If that works for you guys.
Okay, I'm gonna step out for a bit, but you guys go. I'll be back probably.
Yeah. Okay. And then who's our friend? I apologize. I don't know.
Yeah, I want to introduce Oakley. So Oakley is a past student of mine who is just finishing up his master's here in BC.
Wow. Hello there. Hello.
Hello.
I'm a math.
You sound like you're inside like a cave or something, Oaks.
Oh shit.
Let me crank you up.
Oh, let's go. Sorry, I wasn't really following the Funny Bunny video because I joined like after the entire thing was already like well going. I had no idea what was going on, and I started playing a chess game, and that's why I was. Oh, my audio was probably weird.
I think your audio is a little bit better now.
Oh, good. No, it was probably because of the fact that I was very focused on my chess.
Mm.
But
as you do.
Congratulations.
I won my game. It was nice. I got a brilliant move. Oh, okay, maybe I didn't. Oh well. Okay.
So the real question is, are you ready to watch this video with
ready.
Aleph and I?
Yeah.
Yeah.
I don't even know if I've learned about Dedekind cuts, to be honest. So
Dedekind cuts?
I'm excited about this video.
This is cool. This is gonna be cool. Huh.
I have a book.
Dedekind cuts?
Oh, that is so sick.
I think
that's so cool.
this is infinities. We're gonna talk about infinities. Is the gist?
Oh, that's coming up for sure. Dedekind cuts are here.
Yes.
I mean,
all right.
Dedekind cuts aren't necessarily, about infinity. They're about constructing the real numbers. But hey, set theory, you 9 times out of 10 are going to talk about some sort of notion of infinity. So
Yeah.
no, I'm actually so hyped for this.
Do you want to cover this one then? Because it seems like it's right up your alley if you know anything about this. More about this.
I mean, it's been a while. How do you mean by cover it?
I mean, just let me know if you want, like, pause it or whatever the case. But like, I think we've been matching the flow. It's been like, oh, let's talk about that.
Okay.
Yeah. So I give you a chance to like speak.
It's been a while since I've looked at this crap, but it's really neat.
I'm kind of curious about this one a lot.
Normally, what you do is to construct the real numbers, you just you've constructed your rationals. Let's assume the rationals are already done being built. Normally what you do is you just take Cauchy sequences on the rationals and say that if 2 Cauchy sequences are like, have distance between them going to 0, then they're equivalent Cauchy sequences. And then that gives you an equivalence relation. And then you basically just say that each real number is a different equivalence class on the Cauchy sequences of real numbers. Or on the Cauchy sequences of rational
Which means what?
So it's like, okay, think about all the different ways that I can approximate pi with a rational sequence. I can start with its decimal expansion. I could start by adding some other...
It's infinite fraction.
Sum where everything in there is an integer over an integer. there's a zillion and one ways that I can approximate pi with fractions of integers. Put them all together in a giant equivalence class box. In a giant congruence class. That congruence class of all those Cauchy sequences that are more or less defining pi are pi. Pi is a set of equivalence classes. That's the normal way that you do it with Cauchy sequences. But Dedekind cuts
Hurts my
are a
brain.
very
That hurts my
edgy way
brain.
of doing it. No, the Cauchy sequences way is like, it's probably more intuitive, to be honest. The Dedekind cuts, it's like all the rationals up to some largest rational is more or less giving you the real number that is like the supremum to that set of rationals. That's the goal. So that each real number is going to be like the supremum to a set of rationals. That's kind of the idea. That, if I remember right, I could be totally wrong. We'll have to find out from the video. But this is like...
Or maybe they'll introduce it in a different way.
That made a lot of sense. That made exact sense to me. That was really good, Oakley. Wow.
Thank you.
Yeah,
No,
congratulations.
this is like I did one what do you call it?
You did like
Seminar?
measure theory or something, didn't you?
No, I'm working on some measure theory stuff for my research now, but it's more on the probability side. So it's not as much about like defining integration. It's just about calculating expectation with it on like funky measures. But yeah, no, the Dedekind cuts are sick.
Let's dive into it, Al. Let's go. Let's do it.
Yeah.
Where do real numbers come from?
Your
What
mom.
I learned in middle school was the real numbers are like the rational numbers, except they also include the irrational numbers. It's very helpful. But one day, during what I can only describe as a mathematical midlife crisis,
Gets
I
bonus points
realized
for
I
being
had a problem with all of this. Sure, I understand that x squared equals 5 has no rational solution. But does that mean it has an irrational solution? Who says it has a solution at all? Are we
The
allowed to
lines
just
aren't lining
invent
up.
a new kind of number just because we really want to take square roots? And later on in real analysis, I learned that the real numbers are supposed to be like the rationals, but better. They have
Immediate
this
bonus
magical
points for
least
having
upper
a
bound
base.
property, which is the backbone of half the course.
Having a face.
But again, who says such a number
It's a
system
base.
exists? Does it contain the rationals? Does it behave similarly to the rationals? How does this all work? This is where many students meet something called a Dedekind cut,
That's an exacto
which
knife.
sounds like a painful surgical procedure, and the way some textbooks present it, it turns out to be pretty accurate. And at best, it just seems like some sort of mathematical formalism used to justify the real numbers with no real insight. But Dedekind cuts are not arbitrary. They're not some weird technical sideshow. By the end of this video, I will convince you that these are a really natural way to define real numbers that make perfect intuitive sense. Now, how did I get to this point? In the midst of my despair, I went to Nick, our resident animation wizard and mathematical grown-up, and I poured my heart out to him. I told him I wasn't sure I believed in real numbers, and the more I thought about it, the worse things got. I wasn't sure I believed in rational numbers either, or negative numbers, and in my darkest moments, I wasn't sure I believed in zero. I told Nick I was comfortable with positive integers, and that was it. Everything else had to earn its place and justify its existence.
What?
So in this video, starting with just the positive integers and some basic set theory, Nick and I are going to rebuild the entire number line.
Can we pause?
First, we'll construct the signed integers.
Yeah.
So when he says he believes in the whole positive integers, he's probably either referencing the fact that he knows about the piano axioms. If you haven't seen those before, I highly recommend looking those up. But there's another way that you can do it. You can actually define the integers in terms of sets. You can the positive integers, the whole including 0. You say that 0 is the empty set, 1 is a set containing 0,
The
2 is
successor.
a set containing 0 and 1, and you've just built counting. And you've kind of ingrained it into the definition of the naturals. And he probably just doesn't want to go into those details for the purpose of this video, but you can actually show that set theoretic construction of the naturals does in fact satisfy the Peano axioms. And so you do actually have the same system coming out of them.
Yeah, that's because like this whole like intuition is trying to build like this is like building like real numbers. This is like justify like as far as I understand history wise, like Dedekind himself was one of the first ones to like invent infinity in a way that makes sense. And then there's this other thing with I think it wasn't Cauchy, I think it was Cauchy. And then they got into a little dispute, and then eventually that became our standard for like describing real numbers now. But Dedekind cuts were like a description going from like what everyone was agreeing on at the time, which was like these integers and whole numbers, and even negative numbers, and technically like irrationals, but not necessarily irrationals. There's special ones like pi and stuff like that. But this was like the intuition is like, okay, we're gonna start from the basics, and then this is how one would construct it, right? That's the idea.
Yeah. No, Richard Dedekind wrote a book called "What Are the Numbers and What Should They Be?" or / "What Should They Do? What Should They Make?" It was written in German, so that's why the translation's kind of odd. But you're definitely right that he was one of the pioneers into like thinking about a lot of these things.
Yeah. So I want to see how we cut this piece of metaphorical pie.
Yeah, sorry.
No worries. Also, I'm going to crank up the speed a little bit so it's just a bit faster. Let me know if you want me to cut it off. All right?
Go for it.
You're good.
All right. Von Neumann.
Then we'll construct the rational numbers. Then we'll see why the rational number line still has holes in it, even though it's dense. And finally, we'll use Dedekind cuts to construct the real numbers in a way that actually matches our intuition.
Yeah, there we go.
By the end, 0, negative numbers, fractions, and irrational numbers will no longer feel suspicious. They'll seem inevitable. And as a bonus, we'll prove that 13 really does have a 7th root, which is good because I've been very worried about that lately. So let's get started.
I'm concerned for
I
him.
believed in the positive integers and some basic set theory. How was he going to invent signed integers? One approach you could take is to represent signed integers as ordered pairs of positive integers, where the idea would be that 5, 3 represents 5 minus 3, which is positive 2, and then he could use 3, 5 to represent negative 2. 7, 7 would represent 0, and so on. Now in this system, he could represent positive 2 many different ways, and in fact, every integer could be represented in infinitely many ways. Now this presents a couple problems. The first issue is that it seems wrong to have multiple ways of representing the same integer. And how do we know if 7, 10 is equivalent to 14, 16, for instance? Or in general, how do we know if a, b is equivalent to c, d? And if we're going to start using ordered pairs to represent positive integers, do these new positive integers behave in exactly the same way as they used to? How do we add them or multiply them? How do we know if two ordered pairs of positive integers represent the same signed integer? Well, it is tempting to say that we can just check to see if a minus b is the same as c minus d, but the whole reason we're in this mess is that due to my existential angst, I don't know what it means to take 7 minus 10 or 14 minus 16. But since Nick already knows where this is all going and he remembers his basic algebra, he can just say that these ordered pairs are equivalent if and only if a plus d is equal to b plus c. So 7, 10 is equivalent to 1, 4, but it's not equivalent to 4, 1, but 4, 1 is equivalent to 5, 2. Now it's easy to check that this relation is reflexive, symmetric, and transitive, so we know that it partitions the set of ordered pairs of positive integers. So the way we represent, for example, negative 3 isn't just 10, 13, it's the entire equivalence class that contains.
So, yeah.
What you do is you say, okay, I want a minus b to be equal to c minus d, but I don't know minus, but I know plus. So then you add, you have to show the audience what you're doing. You have to add the c to both sides and then add the d to both sides to explain why my equivalence relationship is kind of doing the same thing that the subtraction rule would if I had subtraction. Does that make sense?
Yeah, it's using the definition of addition, right? Or yeah, I guess the definition of subtraction in terms of addition. Yeah.
Yeah, I would have liked to see that a little bit more explicitly as a viewer, and I'd also I would rather him show me the intuition of what's going on than tell me that an equivalence relation is reflexive, symmetric, and transitive. I would want him to tell me it's an equivalence relation, which mathematically means we can treat them as the same thing.
Yeah, that would be, because I think the next bit we're going to get into right now is like those sequences. Like it's an infinite number of them, but if we can show that this set is the same thing as gets the same solution, then it's defined as it. Right?
I don't think he's going to use the Cauchy sequence definition though.
No, because these are whole
this
numbers.
Is really cool. I've actually ever seen the negative integers created this way.
Really?
Yeah.
This is what Wayne and I did, and when I took that set theory directed studies, we built everything.
Sounds like
fun. Okay.
This
was a lot of fun. I'll tell you more later.
This was making sense though, like the context we just
10,
got.
13 with a line over it, which of course is the same set as 1, 4 with a line over it, which is the same as 5, 8 with a line over it. And
so
likewise, each representation of an integer corresponds to an equivalence class of these ordered pairs. None of these classes overlap, and in aggregate, they contain every possible ordered pair of positive integers. The next issue is figuring out how to add and multiply these classes. It turns out that addition is easy. If we want to add a, b to c, d, we just add component-wise and get a plus c comma b plus d. We can check that this corresponds to the algebra we knew 10 minutes ago and pretended to forget. But we have to check to make sure this all makes sense. Let's say that instead of using a comma b as a representative from that equivalence class, we use a prime b prime instead. And the same for c comma d. For example, if we wanted to add 6 comma 10 to 7 comma 1, we get 13 comma 11, which matches Nick's assurances that -4 plus +6 is +2.
Holy smokes.
But if we swap out the first pair with an equivalent one, say 10 comma 14, and we replace the second pair as well with an equivalent pair, say 9 comma 3, and add them, we now get 19 comma 17. But notice that this matches our previous answer, since 19 comma 17 is equivalent to 13 comma 11. In general, if we want to add the classes corresponding to a comma b and c comma d, we get a plus c comma b plus d. But if we use two equivalent representations of those classes, we get a prime plus c prime comma b prime plus d prime. Now we know that a plus b prime must equal b plus a prime, and we also know that c plus d prime equals d plus c prime. Add these two equations together, and we get that a plus c plus b prime plus d prime equals b plus d plus a prime plus c prime. And if we group together the terms like this, we can see that a plus c comma b plus d equals a prime plus c prime comma b prime plus d prime. So if we use different representatives from the same two equivalence classes, we get the same result. Now we have to answer the question of how to multiply these classes together. Back in algebra class, we learned that a minus b times c minus d is ac plus bd minus the quantity ad plus bc.
I never learned that.
This suggests that I might define multiplication as a comma b times c comma d equals ac plus bd comma ad plus bc.
So this is just algebra
Again,
then, right?
We have
Like,
to
we
make sure
can
this makes
skip a
sense
little
when we
bit of
swap
this.
in different representatives for the same equivalence classes.
Oh, yeah.
Let's say we swap out a comma b with an equivalent ordered pair a prime comma b prime. We'll show that if we swap out an equivalent representation for that first number, we get the same answer. You can just as easily show that we can swap out an equivalent representation for the second number too, and therefore we can swap out both numbers consecutively and be confident that we'll get the same answer. Let's quickly write out this proof. We can actually carry out the multiplication the way we defined it earlier.
Well, this is
and
like a
we can see if
lecture
these two
though,
equivalence
isn't
classes
it?
are equal. So to check this, we add together the two outer terms, rearrange a bit, and factor, and we use the fact that a prime plus b equals a plus b prime. Multiply out and rearrange, we get the sum of the two inner terms above, which tells us that yes, the two equivalence classes are the same. Now we should check a few other things. For instance, if we just take two positive integers and add them the way we already know how, and then we turn each of those numbers into their new representation as equivalence classes, and then add those two equivalence classes, we indeed get the representation of a plus b. Other things we should check. If we take the equivalence classes corresponding to 5 and 7, for instance, and multiply them
Okay,
together,
why are
we
we
get the
checking
equivalence
all
class
these
corresponding to
things?
35. We should
Because
check the
we're
usual
building up,
properties of
Addition, multiple.
0 and 1
We're
work
building a
just as we
field.
expect, even on negative numbers.
I guess so.
None of these are hard to prove. They're just a bit tedious, so we're going to skip over them. It's easy to get lost in the weeds here, but let's take stock of what we've done. We started with positive integers and the usual addition and multiplication
We're already
operations
in
on
the
them.
weeds.
We created these new
We wanna
entities and
pause
gave
real
them
quick?
cute little names like
Yeah.
-1, 0.
Yeah, what's up?
So the motivation is that you don't know that multiplication distributes yet. You don't know that you have additive inverse. You don't know any of these things yet because you're just building them from the start.
Right. I guess, but what I'm asking is like, yeah, we have a bunch of these equivalence classes. I guess it would be nice to be able to add and multiply these things because then you have the semblance of a field structure, right? So like what he's trying to do, he's
You would get a ring.
proving that Z is a field by doing this stuff.
No, you'll get a ring, not a field.
Oh, a ring. Yeah, you're right. Yeah, sorry.
Yeah.
Sorry to be the
I'm actually.
No, you're absolutely right. It's a ring, right?
Yeah.
Yeah,
The point is,
I'm actually.
the point is like intuitively we kind of understand that once we've defined things in a way that we know we'll do what addition and multiplication do, we could probably just go home. But like we need to. This is actually plot building what he's doing. There's a big problem with the Dedekind cuts. Is it's kind of annoying to add them and to multiply with them and recover addition and multiplication on the reals, where it's a lot easier to do it for Cauchy sequences. Addition and multiplication with Cauchy sequences, with that definition of reals, is way more intuitive, I think, and a lot of people have said that. So he's kind of like pointing out that the way that we choose to define our integers is going to affect the amount of work that we're going to have to put into proving they behave the way that we think they should.
Okay.
So it's plot building, I
I
think.
also kind of feel like it's very. I haven't seen anybody else do this, but he was like, let's just forget that we know anything about anything, right? So like we have to show that these exist, otherwise they won't exist, which is why he's being like so thorough about all the properties.
There's a philosophical reason for that, but he doesn't want to give a philosophy video, which is why he painted it as I'm having an existential midlife math crisis, which I think is hilarious and effective to do for a video because it does kind of make it entertaining and it makes it kind of curious. But the philosophical reason
It's historical,
is
right?
that
And bro's just gonna drive by in a Mustang in 5 minutes.
it goes back to Russell's paradox. Like Russell's paradox basically broke all of math. And so we need to start at the very, very bottom and very cleanly and tediously work from how do we axiomize the existence of sets? What are we allowed to do with sets? How big can they get? To prevent the existence or to prevent the existence of a set of all sets which do not contain themselves from being allowed to exist. Like if that, as long as that set doesn't exist, we don't have Russell's paradox and math doesn't fall apart.
Yeah, I guess my question was just more like I just wanted to know what he was trying to do, and I guess he's trying to create like this ring structure, right?
Yeah, he's trying to create the ring of integers, but from scratch.
Yes. Yeah.
Also, like in a more intuitive sense, it's just like he knows that he wants to eventually get to the reals, right? So like anything we can do there, like we should be able to get. So like that's probably what he's gonna say is like, oh well, now we can, do division. Now we can do, so maybe not like necessarily just a field or a ring structure or whatever. Like the bigger picture is just like, well, I want to be able to do all the stuff we can normally do.
Yeah, those called extensions, field
he's gonna
extensions.
run into that division problem right away, isn't he?
Yeah.
Yeah. He's also showing you the brilliance of the Dedekind cuts because the way that we construct the integers and the rationals are like conceptually the exact same. And then you try to do that sort of thing for the reals and you're like, oh, this isn't working very well. I don't know what to do. And so the Dedekind cuts are a very creative solution. So he's kind of showing you that it's like, yeah, we can do this. And oh, we'll do it again. And oh, let's do it one more time. Wait, we can't. We need to get clever. Boom, Dedekind cut. So he's kind of setting the stage for them to seem as fascinating as they are to the audience.
I could dig it. I think it's a little slow with the proof stuff though, but I mean that's the point, right? Is that it's building everything up.
I think he should hand wave a couple of the proofs and just state we can prove this and give like a rough gist of it.
Yeah. We could save time by saying algebra comes out like this, and you just show like step by step by step, like animate it. That's the kind of thing you would animate.
Yeah, you can do an example of like one proof and say, here's an example of how we would prove the commutativity. We can prove associativity and it looks pretty much the same. So we won't, we'll skip it here, but it looks pretty much the same.
Leave it as an exercise for the reader.
Yeah.
Maybe
oh, hell yeah.
I kind of like that he's going through everything.
No,
like,
it's not.
The vibe of the video is not like a cereal breakfast, I watched this in like a couple minutes kind of video to me, but I think it could work well in another format as well.
Not true.
Yep.
Agree.
Okay, let's press on.
Yes.
So +2 and so on. And the new entities corresponding to our old positive integers behave just like the old ones did. As a physicist would say, there's no experiment you can do that can differentiate between the old and the new positive integers. To make things even better, these new negative numbers, and what we're calling 0, behave in exactly the way we want. So I think it's fair to say that we've constructed the integers out of just the positive integers and some sets. And if you followed this so far, I have some good news. The constructions that follow are actually simpler than this one, and they have a more intuitive structure to them.
0 is going to be weird.
Now that we have the integers, how do we construct rational numbers? The straightforward answer that may have occurred to you is to represent a rational number as an ordered pair. And of course, there are multiple representations of the same rational number, so we have to take all of them. You'll remember from algebra class that a over b equals c over d.
Oh yeah,
if and only if
we
a,
have
b
negative
equals b,
numbers
c.
now, right? So you can
Or
use
as they used to say, like about 100 years ago, the product of the means equals the product of the extremes. So we'll say that two ordered pairs are equivalent if the product of the outer numbers equals the product of the inner numbers. And you can easily show this is an equivalence relation, so it partitions the set of ordered pairs of integers where the second integer is non-zero. Now, one weird thing to think about is that in this setup, a fraction is a set of ordered pairs of signed integers, and each of those integers is a set of ordered pairs of positive integers. So a rational number is an equivalence class of ordered pairs of equivalence classes of pairs of positive integers.
Oh, that's
we need
weird.
to define addition and multiplication, and just like earlier, we already know
Can I
we
make
want
it
the answer to
weirder?
be. So we can define the
Yeah,
addition.
hit us with it.
So ordered pairs aren't actually sets, and we want everything to be a set. So there's actually this thing called the Kuratowski definition of an ordered pair, where each ordered pair is actually a set containing the first element, and then it contains a set inside, which contains both elements. So the ordered pairs are sets of sets, and then the equivalence class is a third layer of sets to get to the integers, and the rationals is another layer of sets. Okay, but what are the positive whole numbers? As I was kind of saying earlier, Like 3 is a set containing 0, 1, and 2, but 2 is a set containing 1 and 0, and like it just gets nuts. Like it's all
kind of
sets.
silly.
It's like 30 layers of set brackets is what you're looking at, really.
Really?
Oh yeah, it's real neat.
Do you get to proving derivatives at that point? Oh my gosh. Can you prove calculus with just set theory?
Math
this is
become like
yeah,
just 10,000
absolutely.
curly braces.
Yes, absolutely. The real numbers are going to be a set of, the way he's doing it here, they're going to be unbounded below sets of above bounded rational numbers with no greatest element. So real numbers are sets, and functions are really just collections of ordered pairs which map input to output. So you put the input in the first component, the output in the second component. So a function is really a collection of ordered pairs, which means it's a set of sets with this 𝖘𝖔𝖈𝖎𝖆𝖑𝖘 crap going on. And then what is a derivative? Well, it's just an operator mapping some functions to other functions. So you take the set of all functions, which there's an axiom that allows us to do that, because it'll be less than the power set in card, because it's the power set, really. Really, the power set is a set of all functions with like some restriction to make sure that outputs are anyway, so the derivative ends up being a set of functions that map the input function to its derivative. And then those functions themselves are sets of ordered pairs with input and output mappings. So yes, derivatives are sets. And so are integrals. I just don't know how, but I'm sure they are.
That's amazing.
I have to think about that one. I guess integrals are the same idea. They're operators.
Yeah, huh?
An integral is an operator the same way that a derivative is. So it's just literally the set theoretic inverse of the derivative should be the integral.
Pressing on.
Well defined.
Yeah, sorry.
This is
No,
just
it's
like
good.
you'd expect, and do the same for multiplication. We don't have to make sure these operations are well defined. In other words, if you use two equivalent representatives of the same equivalence class, you get the same answer. It's a good exercise to write out these proofs, but we won't bore you with this.
You just did.
Now, just like earlier, we should make sure that these new objects behave the same way as our old ones did.
At least you're
We should
skipping
also check
these
the usual
ones.
properties of rationals,
Yeah.
like commutativity and associativity of both operations, and that multiplication is distributive over addition. And we can even show that our new set forms an ordered field. What's a field? It's just a set with two binary operations that behave very nicely with each other. We'll list out the properties, but honestly, whenever I try to remember what they are, I just mentally run through the properties that Q has. And an ordered field is a field with a relation that we'll call less than, which has the usual properties that we're used to from dealing with rational numbers. The one that might look unfamiliar is trichotomy. This means that if you take any two numbers, they're either equal or one is less than the other, and furthermore, only one of those is true. How do we define this relation in the case of the rationals? We can just say that x is less than y if 0 is less than y minus x. And we say a rational number is positive if it can be represented as an ordered pair of two positive integers. And of course, to be thorough, we should check to make sure that this definition of less than complies with the requirements we have above. And we should make sure that these new whole numbers, which consist of an integer paired with the number 1, still behave the same way. Now for the main event, how do we construct real numbers? Now, it's worth asking if rational numbers are really missing anything. You might argue that since the square root of 5 isn't rational, there's some other irrational number whose square is 5. But my question is, who says that 5 really has a square root? If no rational can be squared to get 5, then maybe that's the end of the story.
Ooh.
But it occurred to me one day that there's a very good reason to believe in the square root of 5. You can partition the rationals into two parts. The first part would have all the negative rationals plus the non-negative rationals whose square is less than 5. And the other part would have all the non-negative rationals whose square is greater than 5. So if I can tell you all the numbers less than my mystery number, and all the numbers greater than my mystery number, I think it's fair to say that this number is in some sense real. In fact, that's exactly how you can construct the reals. You can just say that a real number is a partition of Q into a lower half and an upper half.
Oh,
This
that's
type
for
of
the
partitioning
cut.
of the rationals is called a Dedekind cut. Now, there's no reason to carry around two pieces of Q if one is just all the stuff to the right of the other, except for possibly the point in the middle, so we'll just work with the left half. So we'd love to define a cut as all the rationals less than a given real number. But this is a circular definition since we haven't yet defined what a real number is. Let's try again to describe this just in terms of the rationals. We want to say that a cut of the rationals is the left half of the number line if we break it somewhere. So the first requirement is that we don't want our set to be the empty set, and we don't want it to be all of Q. That's because the empty set would have to represent negative infinity, all of Q would have to represent positive infinity, and we do not want to include those in our construction. Next, we need downward closure. That is, anytime the set includes one rational, it also includes everything to its left. Finally, we don't want it to have a greatest element. In other words, it does not include its right boundary. So for instance, the negative rationals form a cut. If we include 0 in that set, it now has a greatest element, so that's not a cut. And the open interval from -1 to +1 is not downward closed, so it's not a cut either. If you give it some thought, I think you'll agree that this captures our idea that a cut should consist of every rational number to the left of some imaginary boundary. Now the idea is that each regular old rational number would be represented by a cut that just consists of every rational number to its left. And if you want to represent something else, like the square root of 5, you would take everything to the left of where this purported number is supposed to be. Anytime you have a hole in the rationals, just grab everything to its left, and that's how you can identify the hole. Now, the super cool thing is that we can define one cut to be less than or equal to another if the first is a subset of the second, and it's strictly less than if it's a proper subset. And oh yeah, we should explain how to do basic arithmetic on these new objects. Addition is easy, just add together every pair of numbers from each cut. You can show pretty easily that this gives the expected result for rationals. If I take each of the rationals to the left of 1 and add them to each of the rationals to the left of 2, I get all the rationals to the left of 3, and only those rationals. A good, though mildly annoying exercise is to show that the result of adding 2 cuts gives us a new cut. For multiplication, well, let's start with multiplying positive numbers. And by positive numbers, I just mean cuts that contain some rationals greater than 0. To multiply them, we multiply together every pair of positive rationals in our 2 cuts and take everything to the left of that. You can then write down rules for handling a negative times a positive and a negative times a negative. And at this point, a good analysis student is itching to show that this process of multiplication gives us a new cut and that the rational numbers still behave the way we want. And there are a zillion other things to check at this point. And while it is tedious, I hope the general idea is clear. These cuts behave just like you'd expect real numbers to behave, and they behave exactly as rationals already do behave. So we've constructed an ordered field that contains things that behave just like rationals, but they include these other things as well, which we're calling holes in Q, otherwise known as irrational numbers. But before we declare victory, we should ask, does this new set have the least upper bound property? That is the whole reason we're here today. Recall that this property says that if we take a non-empty set of these elements that has some upper bound, then there must be a least upper bound, though possibly not in our original set. So for instance, in Q, the numbers strictly less than 1 have a least upper bound of 1. But the whole problem with the rationals is that sets like this one don't have a least upper bound. But it's actually really easy to take the least upper bound of a set of cuts. Just take the union of all those cuts, and you get a new cut that by definition contains as subsets all the other cuts. It's not tough to show that if your initial set of cuts is non-empty and bounded above, then the result of this procedure is a new cut that is actually the least upper bound. I love this construction because the final step seems simple once everything is set up right, but historically it took mathematicians a long time to get all this organized and straightened out. Okay, you want the basic idea behind the proof? First, it's a straightforward argument that when you union together a non-empty set of cuts, you in fact get a cut, unless you end up with all of Q. Since there's an upper bound to all these cuts, that means there's a rational number that is not in any of them, so our union can't be all of Q. Now we have to argue that this new cut is in fact an upper bound, but that's simple since it contains every one of those cuts as a subset, and that's what it means for one cut to be greater than or equal to another. And finally, to show it's the least upper bound, imagine you took a smaller cut. Then it would be missing some rational number that was in the union, but that means it's absent from all of the C sub alphas, so it's not an upper bound at all. Now what if we want to take the 7th root of 13? We can just look at all the positive rationals whose 7th power is less than 13 and take the least upper bound. And instead of least upper bound, we write sup, which stands for supremum. This does leave the question as to whether this really works. We know there is definitely a least upper bound of this set, but does this number raised to the 7th power actually give us 13? Well, it does, but the proof takes a little work, and I've already been talking a long time, so we'll put it in a separate video. The important thing to remember is that we can construct the reals in a fairly intuitive way from the rationals, and they have the least upper bound property. The rationals can be constructed from the integers, and they form an ordered field. And the integers can be constructed from the positive integers, just like we promised. And oh yeah, I do once again believe in the number 0.
Okay,
now
glad
bonus material.
You believe 0.
When I took complex analysis, we learned how to compute some really tough-looking integrals on the regular old real numbers, but we used complex analysis to do so. I started to wonder, what
residues.
Imaginary numbers? Is the argument still valid? Yeah. Is the answer still pi over 2? I quickly realized that if I didn't believe in the imaginary or complex numbers, I could fudge it. I mean, I could construct the complex numbers. It's worth taking a moment to think about how you would do this. What's interesting is that this might be the simplest construction in this whole video. We can use ordered pairs of reals to represent complex numbers. We can then define addition in the obvious way, and define multiplication in a not so obvious way, but it corresponds to the rules you already knew for complex numbers. You'll want to check that numbers of the form x, 0 still multiply and add like real numbers, and you'll have to check to verify about 100 other properties. And that's really all there is to it. You don't need to believe much of anything to solve that integral, even if you have to use imaginary numbers. Thanks for watching, and we hope we've made Dedekind cuts and the construction of number systems more intuitive. Nick really wanted to be here to thank you himself, but he is in my closet computing the decimal expansion of the 7th root of 13, and I may have locked the door from the outside. I told him he could come out when the digits start repeating. As an aside, he's a super smart guy, but he takes forever with the simplest arithmetic assignments like this one.
Wow.
Anyway, if you've enjoyed even a single moment of this video or any of my t-shirts, please click like and subscribe. It really helps us out. I'd like to thank Grant Sanderson and 3 Blue 1 Brown for hosting this contest and for single-handedly making math videos cool. We'll see you next time.
Wow.
Okay, baller video, my only complaint is that he constructed the complex numbers like in the easy way.
There's a hard way to do it?
Hard way.
It's like you take equivalence classes of polynomials modulo x squared plus 1.
Oh my god, it's the fucking other video.
X squared plus 1.
Was that you talking about that in chat earlier?
They're all tying together at least. This set of videos.
It's almost like math is a big canon.
Huh?
We had a good stream of videos today, except for that economics one.
Hey, good thing it was a starter.
Economics
Got
one
that
is
out of the way
crazy.
early.
Yeah.
Wow. I think I'd say this was like a very good video. Like it wasn't. I wouldn't say this is like outstanding in terms of like visuals, but like in terms of just like genuinely understanding it, like the
No, this is a
material.
beautiful video. The
Yeah,
fact that he had
I would say this is a
a
9.
voice and had like expressions on his face makes it so much more engaging to an audience member. To be honest.
Yeah, true.
I think just like he had an extremely elegant way of doing it. Like there has to be almost no one probably who talks about it this way, and that's why for me like it's very up high already because it's like he made it sound like this is like the natural way to explain this, and I'm assuming that this is not a common way to talk about it.
Well, to be fair, this is like
But
tried and
he
true
explained it, like-
because historically this is like what had to be figured out because of the whole conundrum with like what you said with Russell's theorem or Russell's paradox you said, and introducing reals into like modern mathematics. So like Dedekind had to like explain this to other mathematicians, and I'm sure it's like been ironed out to such a degree that now it makes there's a formal way to like describe it, and this was like very clean because of it. Because all of modern mathematics would not be described unless we got this far with the
Yeah, I
Dedekind
just think
cuts.
that like fully working through the construction of saying like I don't believe negative numbers exist. I think that's probably not something that people do every time they do this, and so I feel like that, like making the decision to do that and go through it in like, because like I don't do this kind of stuff, but I was like, oh, I totally get what's going on, like completely.
I
Oh,
would have
fair.
put maybe an extra minute or two into like trying to motivate the philosophy and trying to say that like trying to like paint a mystery to really engage the audience of this huge problem that math has with Russell's paradox at the core, and anything can be proven true and false if we allow Russell's paradox. So we have to use axiomatic set theory to. Oh, I think that's a 10.
I'm on the 9.
Oh, it's like a 9? What the?
Yeah, it's 1 to 9.
So I could have seen a little bit more of that motivation of the philosophy, and to save time, I would have spent a little bit less effort on the proofs for the first case. I would have done like one proof. These are the definitions, and I would have drilled straight to Dedekind cuts. And I even might have spent 20 or 30 seconds saying that like you can construct 3 as a number out of sets as like an example. Like I would have done like 2 or 3 examples of that without all the extra notation. Like I would have started the story where the story starts. He kind of like this whole thing.
Or he could have made a comment too, right? Saying like, "Hey, this is how the story actually starts. We're not going to do that. I'm going to start, with the basis of thinking that the positive integers are real, right?"
But I'm just like thinking for like an audience member, I think you can create a more interesting hook if you actually follow the story more closely. Because it really is a fascinating story. This like problem that shows up in the middle of the 18th century that explodes math, collapses it, causes mathematicians to argue with one another like their lives depend on it for like 20, 30, 40 years.
I'll say that
Yeah.
when I got taught like anything with Fourier or like Heaviside, like it was motivated like that, where it's like, oh, this like big, commotion like happened, and then these ideas were really explored, and I found it like just completely boring to me because I was like, well, clearly people have like figured it out, like, and I'm not a mathematician, so I personally really like that he was like, let's ask a question like, how do we think about math without like these things that we think are really normal to math? Because I feel like for me, as someone who's not like into the paradox stuff, I was like, oh, this is really relatable, because as soon as you start talking about math history, I'm like, well, I'm interested in it, but it's like, that's history. Like I care about doing mathematics now,
Yeah, I guess I gave you a red herring. It's not so much about the history. It is about the fact that there is like this massive problem in math that like means, if we don't fix it, then nothing is correct. Anything can be proven both true and false. But I see your point. Not everyone in the audience is going to have the same interest in the.
I think you might also have to like explain like why, like spend a fair amount of time like kind of setting up like why that's even true. Because my first question is like, well, what do you mean? Like numbers exist. How would they not exist? You know?
Yeah, 2 apples, and
Yeah,
then it gave
yeah,
me 2 more
exactly.
apples. I have 4 apples. Like, what's wrong with that?
Yeah.
But I guess that's true then. Motivation needs to come from something. In this case, this guy is purposefully framing it as like, I don't believe in these things. These cannot be real, because that's the argument that they had. Some of these mathematicians, they just did not believe in the proof of it until Dedekind. You know, they didn't believe real
That's
numbers were real.
true.
Mhm.
I mean, even in like ancient civilizations, they didn't even believe in negatives. I think
Yeah.
that there's some history of that. There's
Well,
another
and
way to do it. There's another way to motivate all of it by comparing math to adjacent fields. In chemistry, or yeah, in chemistry, when you look at what's going on, you can boil down all of the molecules and everything into atoms. When you take a look at computer science, eventually, at the end of the day, you get down to electronics and circuits and wires. So, what is the kind of bottom line of math? What's the
well,
what's
that's a
the starting
divisive
point of math?
answer, though.
Well,
Pardon?
philosophies.
Jesus.
That's like you're poking a bear with that question, I think.
No, it's very easy. The atoms in math are sets.
Yeah, but some people don't
Everything
believe
is
that.
built on top of set.
Well, that's exactly the way you got to prove it and argue it.
Yeah.
That's because if you accept these axioms, then yeah, then that's if you can prove that I mean, at least on our end, it's not philosophy where it's like they kind of are figuring things out. So most of the time they have
Well, this
logic
isn't
for it.
a research paper. It's a video to, you can make some sweeping claims, and you don't have to prove everything.
Yeah, I think that it felt like this is probably the most neutral take in terms of saying like, well, let's just pretend these objects don't exist, and then let's make a way to construct these objects
Sure.
using some specific parameters. Because as soon as you start to talk about any kind of philosophy or motivation for it, some people are going to go like, well, I don't like that in some way. So I think trying to just kind of approach it as almost just really a pure construction, like, it may not be the most glamorous or like most emotional or anything, but I do think it's kind of neutral for a lot of audiences to be able to relate to in their own way.
What's the title of this video, Aleph?
It says, I stopped believing in real numbers. Dedekind cuts explained.
I'm also biased because like when I started learning differential geometry, I said I don't believe in calculus anymore. Like, what is the way that we construct that from these principles? And that was like, that viewpoint was very helpful to me in like finding things in education, especially with self-study. So like that's my background.
Oh yeah, that's the same idea here. It's like, how do we know? And then, I mean, this is fundamentally different because your background is engineering focused, and you have like actual problems to solve. Sorry, but at least in this end, this is like the basis of the modern mathematics. I enjoy it. I don't know. I see the whole purpose of like the framing, and I can totally understand like for the scope of this video, it's not giving us the history because that's not the point of the history lesson. It's getting to the proof.
I'm not asking for a giant history lecture at all. I'm asking for more motivation because I think you sure, it's fine. You can say I had a silly question or I had this like realistically nobody just stops like believing in math unless they've already seen.
Oh, I do that though. Like when you said like, oh, this guy.
My point is that you'd already gotten to differential geometry level before you stopped believing in math. The vast majority of people out there blindly believe in math because it works, and we have bridges, and we have engineering, and we have computers.
Wait, no, that's a false statement. The vast majority of people out there can't even use math as a tool.
No, that's my point. That's my point. Because they don't understand it, they just blindly accept that it works.
But I think like it was interesting because you were saying that he was framing it as a mathematical midlife crisis. Meanwhile, I was like, oh, I think this dude absolutely went like, I don't feel confident that these things exist unless I prove them myself. And then this was his like, mecca that he did to like,
that's a teaching tool.
And was like, let's go.
Yeah, like I think that's exactly what happened.
Then, because like all I'm saying is that I think that there are more engaging ways to motivate it. I'm not saying what he did was bad or not a good way of motivating it. I just personally probably would have gone a different route. Not even much different, just a slightly different route.
That's fair. That's fair.
Yeah,
like,
and I think like there's always
that point.
Yeah, there's always different ways to approach it, and I think I do think though that like his presenting abilities were like
phenomenal.
Very good. for,
Phenomenal.
for
Yeah, I think
what we've
I agree
seen
with like
so far.
I agree with Hamiltonian. Hamiltonian says like it kind of dragged on a little bit. I mean, for being about Dedekind cuts, I felt like we could have spent a little bit more time on the cuts and the properties of the cuts. Like that was interesting to me, and I was like, oh, and he just kind of felt like he glanced over it, and I was like, join us in the second video, and I'm like, what?
I was gonna
see it now.
I was gonna say Hamiltonian makes a good point because like how many people did believe in real number? Well, ask the Greeks what they thought about the square root of 2. You know, like
You'll just be thrown into a freaking ocean.
that's right. Just scare him with beans though.
I'm just thinking to like what channels like Veritasium and like Vsauce and like even like I guess 3 Blue 1 Brown, like how they spin mysteries together, how they really get you hooked by this like something that just seems unusual and like interesting and like kind of dank. You know what I'm saying? Like they have a good way of spinning a mystery. Sorry, yeah.
Oh, I was just gonna say, yeah, I think it's definitely a different niche than those. Like, it's totally a different audience.
Yeah, but there's a reason why those channels have zillions and zillions of subscribers.
Yeah.
Like, I'm just gonna say it straight. Like, what they're doing clearly is working.
Yeah, I think at that point it comes down to like how you view
sensationalism.
Like, yeah, what we should like be discussing in math, I guess, like what a math video, like its purpose is, and then also like in the context of the fact this is like 3 Blue 1 Browns like contest that we're participating in as well, right? So
yeah, and that's kind of like what I'm going after here is that I do think 3 Blue 1 Brown does the same kind of thing where he like starts a video by giving you this problem, like one of my favorite 3 Blue 1 Brown videos is there's a block that's like slowly moving towards a wall, and it's a heavy block. It weighs say 1,000 kilograms, and then there's a 1 kilogram block that's kind of sandwiched between them, and then the 1 kilogram block bounces back and forth off of the wall and the bigger block until the bigger block and the little block both kind of go away, and you count the number of collisions, and the number of collisions ends up matching the digits of pi. And so he paints this problem at the very, very beginning of the video, and it makes you go, what? Where's the circle? How is pi showing up here? I understood when it showed up in, Fourier series or in complex analysis because, multiplication is just rotation, and that means circles. So, of course, I'm going to see pi. But this problem, it just gets you so engaged and so excited and interested, and you get glued to your screen because it's such a deep, fascinating mystery.
Yeah, I think
so. That's what I'm like. Yeah.
This video is like completely different though because it's meant to say like why like what is a Dedekind cut? Like it's not really a mystery. It's like saying, hey, you've encountered this object or you don't know what this object is, and like let's get to know an object. Like let's really fully understand like how this object exists in our world, which is like it isn't mysterious really. And I feel like the way that he sets it up, it's like it almost feels like mundane because of how simple it seems sometimes, because you're like, oh yeah, of course you just like add these things, like you just do this stuff, but it's like we didn't have that before. Like somebody had to come up with all that stuff.
Yeah. No, so if I'm rating this as like university lecture, I mean, I understand it's not. It's kind of somewhere in between, in my opinion. If I'm rating this as like a university like lecture, like something that's meant to be educational and informative and just tell you how the thing works, 12 out of 10. Like it's phenomenal.
Yeah.
But if I'm trying to compare this to something like a Veritasium, a Vsauce, or a 3 Blue 1 Brown video, I do think that there's just a tiny bit more that can be done to kind of wind up that mystery somehow. Maybe the ways that I propose I don't agree with, but I feel like the average viewer, if they're in like second year math or even they just took their first calculus course,
they would not know what.
Be like, why the fuck are we doing any of this?
Yeah, there's no. You have to like be bought into it. Like that's why I think the video is so good, because I'm like, well, I like to have audiences who are bought in. You know what I mean? Like. But you're right.
Yeah,
it's
we're
not like a
already bought
video
in because we're math nerds.
Yeah.
Yeah.
So
we don't need to
objectively though, it's so
capture our attention.
it's so well done objectively. Like you gotta just be like, fuck,
Yeah.
dude.
No, we're arguing over like a half a point. Like, is it an 8.5 out of 9 or a 9 out of 9?
Well, I think it's a lot of interesting questions because, like, I think at a at a larger scale, like this is the question about being able to rate these kind of videos, and like at some point it does just come down to like, well, like should it be a three blue one brown video, or like is it just a math video that you would watch, and like who's the audience? Because it's a super different like
Totally.
Yeah, I was gonna say because like most of this competition is not trying to catch 3 blue 1 brown style. It's inspiring math videos. Did you get any insight out of it? And there's tons of different directions one can take with it. You can do a physics video, or you can do like a space video. Apparently, economics is on the table. So, so
No,
how
it's not on the
shouldn't
table.
be.
how well can you deliver that? And it's not matching the style, because you can say that the style is good for 3 blue 1 brown, and the reason why 3 blue 1 browns is so good is because it appeals visually. And he actually has an incredibly like diverse audience, right? Kids can learn this stuff, and I've worked with kids that just watch, like they're hyper nerds, they're dorks. So like that's the style that would work with him. And I mean, not every child is going to learn about linear algebra that early or quite understand it, but like because they've watched a video about it, there's some insight. This is definitely like, if those who know about it definitely will appreciate this, right? And I think this is like a fantastic tool for like anything in the future, but this is not for the younger audience, I suppose. It's literally targeted towards undergraduate. So, but does it do what it's supposed to do very well? And I think it does.
Sure. Okay. Then yeah, I think let's just give it the highest we can. Like genuinely, I don't have any other complaints. Like sure, 8.5 out of 8.53. That's good with me.
It's the best. Well,
I don't know if I'd say it's the best, but it's a very good video.
I'd be a little generous. 8.67. Okay.
Bonus points for being jacked.
The being totally ripped.
Constructive feedback. Absolutely fire. Keep it up, my brother.
Yes.
Was lit. Keep it up.
I think the things that y'all said about like not having as long examples are good though, because I do think like generally people probably don't need that much stuff.
Yeah, I think like the only criticism that I have is like he could have spent a little bit less time, I think, on the front end stuff and a little bit more time on the Dedekind cut stuff, because that's what the title of his video is.
Or he should have titled it differently.
Either way, right?
Yeah.
You know, it's not that like I don't believe in the real numbers. It's like I don't really believe in the rational numbers, and then you can go through all that stuff and just like stop at the rational numbers, right?
You just said I don't believe in numbers at all. Where do you come from? What are they?
Sure.
Yeah.
But I mean, I think the point of his video was to introduce you to Dedekind cuts, and I wanted to spend a bit more time there than in the preliminary stuff, I guess.
Yeah, it did feel like a a friend we made along the way, but it wasn't like the main character.
Yeah. So what I'm kind of saying is that if you're gonna only treat it like a main character, then don't title it like it's the main character. Title the video differently, so I don't have like some expectations that never get met.
Yeah.
So like,
I think the title,
maybe phrasing it like proving all numbers exist or something like that. But that's like another kind of like title as well.
Eating the cuts out of the title is probably fine. Like, or like I think Penn said, I stopped believing in the rational numbers is also
real numbers.
I stopped believing in numbers. Period.
I gotta love that.
This is what happened.
I stopped believing in numbers. Period.
What if it was the other way around, where it starts you out with like, okay, we understand what real numbers are, or do we? Like a Vsauce video, or is it?
Or do we?
Are you saying that there's a number where if I keep zooming in over and over and over again, it's gonna keep going? I mean, what does that even mean? We have circles in real life. Is there a theoretical limit atomically? That's the kind of Vsauce bit.
Space in my paper to write out all these digits. I mean, if I can't even write it out, how do I know that it's even there?
Exactly. I've
even real?
scrutinized. What's even a negative number? Are you a number? It's like I think that kind of context. I mean, that builds up what you already know and then scrutinizes it. That's why I like Vsauce
What
style. I
color is
love
the
that.
number 5?
Yes, yes. Are numbers real? They're not unless we cut it. It's like without context, that's good.
I got something for you if you can hear it.
I'm gonna dedicate cut to the chase.
Oh my god.
Sorry, that was terrible.
Bad jokes territory.
Terrible.
Is it not letting my audio get through?
Change your audio settings to like studio or something. You could probably.
I'm trying to play a song. I'm trying to play like I was trying to prank you with like 10 seconds of 𝖘𝖔𝖈𝖎𝖊𝖉𝖎𝖙𝖘.
Oh,
Are we gonna get our streams copyright claimed?
surely not.
Oh
right?
no, I forgot that's even a thing. No, 𝖘𝖔𝖈𝖎𝖊𝖉𝖎𝖙. I think 𝖘𝖔𝖈𝖎𝖊𝖉 was mostly NCS. I could be wrong.
Okay,
But
cool.
he made the Vsauce music.
Okay.
I was
I
gonna
recognize the
prank
name.
surprise you with some of that.
Well, I mean, if Aleph is gonna post this on his YouTube channel, we probably shouldn't be playing those kinds of things.
Yeah,
Well, no,
I'm
I
fully
forgot.
expecting this because we just
It
been.
didn't come through the audio though, did it?
I only heard a second of it, but like I don't think it's gonna get anything. We've been literally
No, I don't
reacting
get
to videos this entire time. I don't even know if that's gonna get through like the copyright like argument.
Oh yeah,
It
it's
probably won't.
fine.
Yeah.
But I mean, we are reacting. It's a live reaction, so if it gets nuked, it's totally fine. It's not. I'm not gonna complain about that. But
You
Yeah.
probably won't be able to monetize, but you're fine.
I'm not.
Instructions.
Still not
Number
monetized on
bracket
YouTube.
62 will shock you.
Number 5.
Imagine if we had to talk about numbers like that, Hamiltonian. I would cry.
Wait, that's awesome.
What's the plan here? It's 5 p.m. now.
Yeah.
Yeah, I'm gonna wait for if I thought Slim was gonna come online around 5, so we could always raid into him once he goes online.
Then I can finish my review of this. I think 8.67 is pretty good. But there's still the other
Did you
things I
let
gotta
us-
finish.
Did you put 6.7 on purpose?
No.
Okay. Just
Yeah.
wondering.
No.
Wait, do I have to go into a website and do a thing?
You do not know.
Oh no, I'm just here for the vibes, right?
You're here for the vibes, and then everyone's just like, we're just giving Aleph
We're just
like
vibing.
some feedback for when he goes to submit the reviews.
Yeah,
We're
because
forcing Aleph to like transcribe, 20 plus minutes of words into the description box.
You went back and forth.
very fun, worthwhile thing. You post 0.67 as an emote. Yeah. You could use my
There's
emote.
the 6.7 emote.
I animated that. I love that thing. It's so stupid.
So dumb and cute. Yeah.
Yeah.
Your fucking bouncy, goddamn Discord reactive thing. Just
Oh,
dumb
yeah.
and cute.
I haven't even seen it on your end. Oh my gosh. Yeah. Who's the next one we would be reading? You said.
Oh, Academy. It's Academy of Useless Ideas. I'll put it into the.
Oh yeah, I always forget that's Slim.
Mm.
I'm like, thanks Academy for the
Type
raid.
that didn't actually type.
Yeah, I haven't seen too many of you guys. So this is like kind of my exposure to getting more involved with that side of the space. Because I think there's only a few guys that I
spelled it wrong.
genuinely-
There should be another E in there. I spelled Academy wrong.
close enough.
We're not like, I don't know, we're not like that aligned. Like some of us are more aligned than others, I feel like.
Yeah. I feel like I LARP too sometimes because I'm like, look, I mean, I don't get me wrong, I love my math, but I'm like, on a whim, ask me to do some derivatives, I'm like, duh. But I think that's like everyone, right?
No, that's what I've spent like a year and a half doing is only derivatives.
You ever go watch Danny's channel? It's like all he's ever doing is derivatives.
It's only derivatives, I
That's
swear.
all it is.
Tangent manifold.
That's hilarious.
Yeah.
Hmm. Okay, well,
more
then I start
numerical analysis, Danny. More numerical analysis.
Oh my god. Dude, that was a dark time in my life.
How far did you get in that?
I had a course on it and it was like, it was bad. It was bad, dude. It was up there with my thermo course, which was also really just god awful experience.
Oh, he's on.
I'll share a story with you, Damie. In my numerical analysis class for PDEs, I hated it so much that my friends and we would just go get drunk before class all the
Oh
time.
my god.
And we'd go to class, wake up the next morning, and I'd be like, I couldn't even read my fucking notes. 'cause
Oh
they
my
were
God.
such terribly scribbled. So I feel your pain. It's like
No,
the
there was a
worst
guy-
class ever.
There was a guy in my PD East class who like pre-gamed like the final, and then he got like the top score on the final.
Oh my god.
That's alternate universe you.
We passed that. I hate class so much.
Numerical analysis is just like the worst. That's why that one video was. I was like, this is a beautiful video because they managed to make it not evil. Like,
They explained what we're doing. I
they
appreciate
said the
that.
words that were good.
The good ones, not the bad ones.
My roommate had asked me to meet her for wings because I don't know, wanted a friend to get wings with. So I'm gonna head out pretty soon here, I think.
Yeah.
Is that
I'm also heading out soon.
No,
you-
that's cool, Oakley. I hope you had a good time, and it was good to hear your voice, man.
yeah, Oakley,
Good luck. With,
very insightful.
Good luck with the Masters.
Thanks, it's been tough. No, I'm really glad. I don't know what kind of chance of luck it was, but of all the videos you've covered, this is the one that I definitely know the most about what's actually going on in the math behind.
Oh, that's awesome.
Good insight. Yeah, no, you really
You
contributed a
want to
lot.
help us with the economics one?
Oh
my
god.
No?
I should just
You
share
wanna see
that.
my bank account balance? I don't understand economics. I understand I'm economically fucked.
Nice.
Economically
Bro
challenged.
has no supply, but all of the demand.
Yeah.
You can probably gonna start a raid.
Yeah, I
Over
was gonna
to Slim whenever you're ready, Aleph.
Yeah, I have it prepped ready to go. So if you want to head over there like right now, you can. But I think you also have to raid as well, right?
Yeah, I'm gonna start the raid right now.
Yeah, for sure. Then shoot, it's been great today, guys. I really had a blast. Wow, this was fun. I'm gonna do the same thing. When you guys are all doing it again different times, right? So I'll probably tune in when you guys can. I'm doing it again next Sunday. So
we're Wednesday or something. Whenever the 25th is.
Yeah, I think we're next Tuesday.
Or
next
Tuesday.
Tuesday.
Yeah, Tuesday. Yeah.
Tuesday.
Tuesday, ain't it?
Tuesday. For sure.
Oh my god, what am I doing? Academy of Okay, I think I spelled it right that time. I keep spelling his username incorrectly. Okay, we're good now. We're good.
All right, we're good. Ready to go. All right.
Yeah.
Then that's it. Then you got everyone have a good day, and then we'll be over on Slim's channel then, right? Slim Shady.
Bye,
Thanks so much, Aleph and Damie. Is so much fun. Like, I had a
Yeah.
blast today. I can't wait to do it again next week.
Let's hang out a different time too. That'd be fun.
Yes.
Yeah, let's play Funny Bunny soon.
Oh my god.
Yes. Yeah. All right.
Candyland.
All right. See you later.
Bye, guys.
Bye.
God.
Okay, that's the raid going.